The expansion begins as a reflex older than memory. A shadow rushes forward, jaws open, and the pufferfish inhales water with violent urgency. Elastic stomach walls unfolding in an instant as its body transforms from streamlined swimmer into spiked sphere. Muscles stretch to limits rarely reached in calm conditions. Dermal spines erecting as the skin tightens over swelling mass. The illusion of invulnerability inflates with it. The puffer does not attempt to flee at first. It commits to defense, trusting in the geometry of intimidation. But the predator does not retreat. Inflation is not a casual trick. It is a physiological gamble. The puffer's stomach, normally compact and folded, expands dramatically as specialized connective tissues allow rapid distension without tearing. Water floods inward through the mouth and gill openings, and within seconds the fish's volume multiplies. The transformation alters hydrodynamics, making it nearly impossible for most gape-limited predators to swallow. Spines that once lay flat against the body now protrude outward, converting smooth skin into a field of sharp projections. The predator's mouth meets resistance, not flesh. This strategy evolved in ecosystems where many predators depend on engulfment. Reef hunters, such as groupers and snappers, rely on suction feeding, expanding their buccal cavities to draw prey inward through negative pressure. A spherical puffer disrupts that mechanism. Its increased diameter exceeds jaw limits, and its spines lodge painfully in soft tissue. The predator may release, deterred by discomfort and inefficiency. For countless generations, this defense has worked often enough to justify its metabolic cost. But inflation is not armor. It is posture. As the predator persists, the puffer's assumptions begin to fail. Not all hunters swallow whole. Some bite. Sharks, with serrated teeth designed for slicing rather than suction, are less deterred by size alone. A determined predator may grip and shake, tearing at inflated tissue despite the spines. The puffer's body, stretched beyond normal contour, becomes taut and vulnerable to puncture. The very expansion that signaled warning now exposes a larger surface area to attack. Inside the inflated sphere, physiological strain escalates. Muscle fibers remain contracted to maintain expanded shape, consuming oxygen rapidly. The puffer's gills, compressed by distension, operate under suboptimal flow conditions. Blood circulation shifts to accommodate internal pressure changes. Inflation cannot be sustained indefinitely. It is designed as a brief deterrent, not prolonged siege. The moment of realization, if one can speak of realization in neural terms, occurs when resistance does not produce retreat. The predator's grip tightens instead of loosening. The puffer, unable to maneuver effectively while inflated, loses the ability to direct escape. Its fins, now splayed awkwardly, cannot generate efficient propulsion. What was meant to immobilize the predator has immobilized itself. And yet the defense was never singular. Embedded within the puffer's tissues lies tetrodotoxin, a potent neurotoxin synthesized not by the fish directly, but by symbiotic bacteria residing in its organs. This compound blocks sodium channels in nerve cells, preventing action potentials and inducing paralysis in predators that ingest sufficient quantities. The toxin does not act instantly through contact. It requires ingestion to take effect. Thus, inflation serves partly as advertisement, a visual warning paired with chemical deterrence. In ecosystems where predators learn through painful experience, brightly colored puffers signal toxicity. A single failed attempt can imprint avoidance behavior in a shark or large fish. This is aposematism in aquatic form. The illusion of safety is reinforced by memory. But predators are not uniform in cognition or tolerance. Some species may sample cautiously, biting and releasing without ingesting lethal doses. Others may evolve partial resistance to toxins through selective pressure. The puffer's chemical defense, powerful though it is, cannot guarantee immunity from predation. Moreover, the ecological balance complicates the narrative further. Pufferfish are not apex predators. They are mid-level consumers feeding on invertebrates and algae. Their beak-like teeth crush hard shells, regulating populations of crustaceans and mollusks. Their survival influences reef composition indirectly by shaping prey communities. If inflation fails and puffer populations decline, trophic cascades ripple outward, altering competitive dynamics among invertebrates. The inflation response itself carries risks beyond predation. If triggered excessively or under stressful conditions, the puffer may inadvertently swallow air at the surface rather than water. Air trapped in the stomach can impair buoyancy control, leaving the fish stranded near the surface and more exposed to birds and surface-feeding predators. Deflation requires time and safety. Without both, the fish becomes an awkward balloon drifting in hostile space. Yet here lies the reversal. The apparent failure of inflation reveals that it was never designed as solitary salvation. It is part of a layered strategy combining morphology, chemistry, and behavior. Puffers are not merely inflatable spheres, they are cryptic feeders, capable of blending into reef textures when calm. Their skin patterns disrupt outlines, reducing detection probability before conflict arises. Inflation is last resort, not first line. When predators persist despite inflation, some puffers exploit the element of surprise within their vulnerability. A sudden, controlled deflation can allow rapid escape through contraction, converting stored tension into movement. The predator, anticipating continued immobility, may hesitate just long enough for the fish to slip away. This tactic demands precise timing and energy reserves, and it cannot be deployed repeatedly. But in rare moments, surrender of posture becomes opportunity. The reef itself also participates in this drama. Inflated puffers wedged among branching corals create spatial complications for predators attempting to maneuver. Spines catch against coral limbs, making extraction difficult. In such environments, inflation regains partial efficacy, not through intimidation, but through entanglement. The habitat amplifies defense. Physiologically, the puffer's tolerance for internal pressure is remarkable. Connective tissues and collagen fibers reinforce the stomach walls, preventing rupture during rapid expansion. Enzymatic pathways regulate electrolyte balance as water floods inward. These mechanisms underscore that inflation is not random swelling, but coordinated orchestration of muscle, membrane, and fluid dynamics. Still, the illusion of invulnerability remains fragile. When a predator refuses to be deterred, the puffer confronts the limits of its design. Defense transforms into liability as mobility decreases and metabolic demand increases. The illusion collapses under sustained pressure. And yet, across evolutionary time, the strategy persists. Why? Because deterrence does not require perfection. It requires statistical advantage. If inflation dissuades enough predators often enough, genes encoding that reflex endure. Failure in individual encounters does not negate success across generations. In the aftermath of such encounters, surviving puffers deflate slowly, expelling water through controlled muscular contraction. Spines flatten, body returns to streamlined form, and the fish resumes cautious navigation of reef corridors. The memory of attack imprints on neural circuits, adjusting sensitivity thresholds for future responses. The reef regains its deceptive calm. Corals sway, invertebrates graze. Somewhere within that mosaic drifts a puffer, appearing docile, almost comical in its compact form. Beneath that exterior lies a system of layered defenses balanced precariously between bluff and biochemical lethality. The fear embodied in inflation is not simply of being eaten. It is the recognition that defense itself can become exposure when it fails. The sphere that promised safety may become a target if the predator persists. And in that realization lies a deeper truth about survival in the ocean. No single strategy guarantees permanence. Every adaptation carries cost. Every illusion carries risk. Yet the puffer endures, a testament to evolutionary compromise. Its defense may falter in individual moments, but across the shifting calculus of reef life, the balance holds just long enough. The reef does not lunge, it inhales. A juvenile wrasser drifts toward what appears to be a tuft of sponge-encrusted rubble, its body flickering with cautious curiosity as it searches for plankton in the water column. Nothing moves except a small, worm-like filament that twitches lazily above the algae. The wrasse angles closer. In less time than a nerve impulse can fully register, the rubble becomes a mouth, the water becomes a vacuum, and the fish is no longer part of the scene. The frogfish does not chase. It does not stalk in the conventional sense. It waits as a piece of the reef itself, a biological impersonation so complete that the boundary between predator and substrate dissolves. Its skin is textured with dermal spinules and irregular flaps that mimic sponges, corals, or encrusting algae. Pigmentation shifts over days to match surrounding color gradients, an adaptive camouflage regulated by chromatophores responding to visual cues. To prey species scanning for movement and contrast, the frogfish is environmental noise. What betrays its presence is a lure known as the elysium, a modified dorsal spine that arches forward over its head, terminating in a fleshy esker. This appendage moves with subtle precision, mimicking the erratic twitch of a worm or shrimp. The wrasse's visual system, tuned to detect prey-sized motion within complex reef backgrounds, locks onto the lure. It approaches not a predator, but an opportunity. The frogfish's body remains still because stillness is the architecture of its strategy. Unlike pursuit predators that rely on muscular bursts over distance, frogfish are built for explosive suction within a confined radius. Their pectoral fins function like limbs, allowing them to reposition incrementally across substrate, but their true weapon lies in cranial mechanics. The skull is loosely articulated, with elastic ligaments that permit extraordinary expansion of the buccal cavity. When the strike comes, it is not a bite in the traditional sense. It is a collapse of space. The wrasse moves within range, unaware that proximity is the final variable required. The frogfish's mouth opens with astonishing speed, expanding to many times its resting volume. Opercular flaps swing outward, and the buccal cavity inflates, creating a sudden negative pressure gradient. Water, along with the prey, is drawn inward in a fraction of a second. The suction event is so rapid that high-speed imaging reveals the entire sequence unfolds faster than many prey species can initiate a startle response. This is the moment of realization too late. The environment changes not through visible attack, but through instantaneous hydrodynamic reversal. The water that once supported the wrasse becomes a force pulling it forward. Escape reflexes, mediated by specialized Mothner neurons in the fish's brainstem, trigger in response to sudden stimuli, but the latency of neural conduction is measured in milliseconds. The frogfish's strike operates within that window, outpacing the circuitry designed to save the prey. Inside the cavernous mouth, inward-pointing teeth secure the fish as the jaws close. The frogfish swallows prey nearly its own size, facilitated by distensible stomach walls capable of accommodating large meals. After ingestion, the predator may remain motionless for days, metabolizing its catch and conserving energy. Its hunting strategy is defined not by frequency, but by efficiency. The terror of this encounter lies in transformation. What appeared inert becomes animate. What seemed harmless becomes lethal. The wrasse did not flee a pursuer. It approached a facade. From an ecological perspective, frogfish occupy a niche of ambush predation that exerts selective pressure on prey vigilance. Reef fish must constantly balance feeding with risk assessment. Overreacting to every piece of rubble would squander energy and feeding opportunities. Underreacting invites catastrophe. Frogfish exploit this trade-off, inserting themselves into the sensory blind spots of prey decision-making. Their camouflage is not purely visual. By minimizing movement and matching the texture of surrounding substrate, frogfish reduce detection by lateral line systems that sense pressure changes. In a reef where currents shift and particles drift, the absence of turbulence around a frogfish reinforces its disguise. It is not merely unseen, it is unremarkable. Yet within this apparent dominance lies vulnerability. Frogfish are poor swimmers, lacking the streamlined bodies of pelagic hunters. Their locomotion is awkward, a series of short hops propelled by modified fins. In open water, they are conspicuous and slow. Larger predators such as groupers may consume them if discovered. Their reliance on camouflage demands suitable habitat. Without textured substrate, their deception fails. The narrative reversal deepens when considering that the frogfish's grotesque appearance, often perceived as a weakness in a world favoring speed and grace, is in fact a pinnacle of specialization. Its ungainly body is an evolutionary investment in suction mechanics and disguise. The very traits that limit mobility enable the instantaneous expansion that defines its strike. Even more intriguing is the frogfish's role within reef trophic dynamics. By preying on small fish that graze algae or consume invertebrates, frogfish indirectly influence coral health and competition among reef organisms. A single ambush may ripple outward, altering the balance between algae and coral growth. The trap extends beyond individual prey to subtle ecosystem shifts. The frogfish's strike is often described as one of the fastest feeding events among vertebrates, but speed alone does not define its impact. It is the juxtaposition of stillness and explosion, of apparent safety and sudden void. Prey species may pass within centimeters repeatedly, habituated to the predator's presence as background. Then, in a moment of alignment between lure, distance, and attention, the reef rearranges itself. The wrasse population learns through attrition. Individuals that approach certain textures or respond too eagerly to isolated movement are removed from the gene pool. Over generations, behavioral biases may shift subtly, favoring increased caution around ambiguous stimuli. Yet the frogfish adapts as well, altering coloration and lure motion to match prevailing prey expectations. It is an evolutionary dialogue conducted in silence. Within the reef's complexity, the frogfish embodies a paradox: immobility as power. It does not patrol territory or chase fleeing schools. It becomes part of the habitat until the habitat betrays those who trust it. Its mouth, capable of engulfing prey with minimal warning, is less a weapon than a vacuum that erases distance. And when the strike concludes, the environment appears unchanged. The rubble remains. The algae sway. Only the absence of a small fish marks the event. The predator settles back into stillness, lure extended once more, waiting for another curious approach. In this domain, fear is retrospective. It is the dawning comprehension, had there been time to comprehend, that safety was an illusion crafted by texture and patience. The trap was always present, embedded in plain sight, and by the time recognition occurs, recognition no longer matters. The ocean tightens before a single tooth is bared. A school of sardines surges upward in a reflexive wave, thousands of silver bodies pivoting in unison as pressure builds from below. The water around them begins to rotate, not chaotically but with intention. Shadows arc through the periphery. A dolphin's flank flashes, then vanishes. Another slices across the opposite edge. The sardines accelerate, but every direction now carries the same resistance. The sea itself is beginning to fold inward. Dolphins do not simply hunt fish. They sculpt the water around them. Unlike solitary predators that isolate an individual through stealth or speed, dolphins operate as coordinated units, transforming open ocean into a dynamic enclosure. Through synchronized swimming patterns and acoustic communication, they generate a containment field of motion that corrals prey into increasingly confined space. The formation of a bait ball is not accidental panic. It is induced architecture. The sardines respond to initial disturbance by clustering tightly, exploiting the confusion effect where predators struggle to target a single fish among many. Collective motion reduces individual risk by saturating a predator's visual processing. Yet this defense contains its own vulnerability. Density amplifies visibility. The school becomes a single entity, a living sphere whose surface reflects light like a mirror. Dolphins exploit this paradox with precision. Using bursts of acceleration followed by controlled deceleration, individual dolphins take turns pressing against the edges of the school. Their bodies move with hydrodynamic efficiency, powered by robust tail flukes that generate sustained thrust. Echolocation clicks pulse outward, mapping the density and shape of the fish mass. Sound waves return with detailed spatial information, allowing dolphins to identify weak points in the formation. As more dolphins join the perimeter, the sardines' world contracts. Escape vectors that once extended into open blue now terminate in muscle and motion. Attempts to break outward are met by swift interception. The dolphins do not need to strike immediately. They maintain pressure, encouraging tighter aggregation. The bait ball grows denser, more spherical, and paradoxically more vulnerable. The fear in this moment is spatial rather than immediate. The sardines are not yet being consumed in large numbers. Instead, they are losing degrees of freedom. The ocean, once vast and multidirectional, now presents only inward-facing boundaries. The dolphin's movement generates a centrifugal effect, herding fish upward toward the surface, where vertical escape becomes impossible. Air forms a ceiling. Dolphins complete the enclosure. The formation becomes a shrinking globe of silver, suspended between sea and sky. Within this sphere, oxygen demand increases as fish maintain high-speed circular swimming. Metabolic rates spike. Lactic acid accumulates in muscle fibers as anaerobic bursts compensate for constrained movement. Gill ventilation struggles to keep pace with exertion. The sardine's coordination, once fluid and adaptive, begins to strain under density and fatigue. Dolphins intensify the containment. One individual may dive beneath the bait ball and release a stream of bubbles, creating a visual and acoustic barrier that fish hesitate to cross. Bubble curtains exploit prey perception. The sudden column of rising spheres appears as a solid wall, further reducing escape options. Other dolphins sweep laterally, tightening the sphere with coordinated arcs. The water vibrates with their whistles and clicks, communication signals that synchronize attack timing. The enclosure is now complete. No direction offers relief. Then the assault begins, not as chaotic frenzy but as calculated entry. Dolphins dart through the bait ball in sequence, striking and emerging on the opposite side. Each pass removes fish and destabilizes internal cohesion. The sphere shrinks further. The remaining sardines compress toward the center, their bodies brushing constantly against one another, scales scraping in claustrophobic proximity. The terror here is cumulative compression. The prey do not face a single attacker. They face the disappearance of space itself. Dolphins' success in this strategy derives from advanced neurological adaptations. Their brains, large relative to body size, support complex social coordination and learning. Hunting techniques are culturally transmitted within pods, refined across generations. Cooperative herding reduces individual energy expenditure compared to solitary chases. Each dolphin contributes to enclosure without exhausting itself prematurely. Hydrodynamics amplify this efficiency. By swimming in formation, dolphins reduce drag and conserve energy, similar to birds flying in a V-shaped pattern. Rotational roles allow individuals to rest briefly, while others maintain pressure. The bait ball persists because the predator's stamina is distributed across the group. Yet the narrative shifts when considering the broader ecological context. Dolphins are not apex enclosures without constraint. Their hunting success depends on prey abundance and environmental stability. Overfishing that reduces sardine populations disrupts this cooperative strategy, forcing dolphins to travel farther and expend more energy for diminished returns. In regions where prey declines dramatically, pod cohesion may fracture as individuals compete for scarce resources. Moreover, bait ball formation attracts secondary predators. Seabirds plunge from above, and sharks approach from deeper water, drawn by vibrations and scent. The enclosed sphere becomes a focal point for multiple species. Dolphins must balance feeding opportunity with risk from larger predators. The enclosure they create can transform into a chaotic convergence zone. The reversal deepens further when observing that dolphins themselves can become encircled by human technology. Fishing nets deployed in open ocean mimic the very strategy dolphins use, surrounding entire schools, and sometimes the dolphins hunting them. Enclosure becomes reciprocal. The hunters of space compression face artificial containment that offers no escape. Still, within the immediate theater of the bait ball, the geometry is undeniable. The sphere tightens. Fish at the core experience constant collision, their sensory systems overwhelmed by contact and acoustic noise. The dolphin's echolocation continues to map density gradients, guiding precise strikes into the most crowded zones. As the mass dwindles, the ball fragments. What began as a coordinated school becomes scattered individuals darting in desperate arcs. dolphins accelerate for final captures, exploiting the breakdown of collective defense. The ocean reopens gradually, but for many sardines, reopening comes too late. When the last fish are consumed or dispersed, the dolphins regroup, surfacing to breathe in synchronized arcs. The water calms, the vastness returns, yet the memory of compression lingers within the ecosystem. Surviving sardines may alter schooling patterns or migrate to avoid heavily hunted zones. Behavioral shifts ripple outward. Dolphins, often celebrated for intelligence and grace, reveal here a different dimension of mastery: spatial domination through movement. They do not rely on venom or camouflage. They manipulate collective behavior, turning defense into vulnerability. The bait ball is not merely a reaction, it is the endpoint of deliberate containment. In open ocean, freedom appears limitless. But freedom depends on available space, and space can be shaped by those who understand its physics. Dolphins harness motion as architecture, bending water into walls and ceilings. The shrinking sphere is both a biological phenomenon and a lesson in coordinated pressure. And as another distant school glints beneath the sun, the pod shifts direction, preparing once more to compress the infinite into a tightening globe of silver. The line breaks. A young seal surges through frigid water alongside its colony, bodies packed tight against the edge of drifting ice, each individual relying on the geometry of numbers for protection. Then the surface detonates beneath it. Black and white forms rise in coordinated arcs, cutting through the formation not to devour indiscriminately, but to fracture it. The seal feels the current shift, feels bodies peel away from its flanks. And in that single disruption, the arithmetic of safety collapses. It is no longer one among many. It is one. Orcas do not begin with the kill. They begin with separation. Within a pod, communication pulses through the water in layered clicks and whistles, each call encoded with information about position, intention, and timing. Their brains, among the most complex in the marine world, support not only individual cognition, but social strategy. When hunting seals clustered on ice floes or fish, schooling in dense aggregations, orcas deploy tactics that aim not at immediate capture, but at structural disassembly. The group must fracture before an individual can fall. The young seal accelerates toward thicker ice, but an orca surfaces ahead, blocking that vector. Another sweeps in from below, releasing a stream of bubbles that obscure depth perception. The seal pivots, but each turn exposes a new flank. Orcas exploit hydrodynamic pressure to herd prey into open water, away from the physical shelter of ice. They generate waves by swimming in synchrony, sending sheets of water surging across ice platforms to dislodge resting seals. Yet even in open pursuit, their primary objective is not brute force. It is isolation. In a colony, vigilance is distributed. Eyes scan in multiple directions, and alarm cues ripple collectively. Once separation occurs, vigilance collapses inward. The isolated seal must monitor every direction alone. Cognitive load increases. Stress hormones surge, altering heart rate and narrowing perception. The seal's muscular bursts become erratic, anaerobic reserves burning quickly under panic. Orcas maintain composure. Their physiology supports both power and endurance. Large bodies insulated by thick blubber sustain energy in cold water, while powerful tail flukes deliver controlled acceleration. Unlike many predators that rely on immediate capture, orcas modulate speed to match prey fatigue curves. They understand, through instinct refined by cultural learning, that panic accelerates exhaustion. The moment of being singled out is not only spatial, it is metabolic. Within the pod, roles emerge fluidly. One individual may drive the prey from behind, another flank from the side, a third wait ahead. This choreography reflects not random convergence, but cooperative intelligence. Hunting techniques are transmitted across generations, forming cultural traditions unique to specific pods. In some regions, orcas specialize in fish, in others in marine mammals. The strategy of separation adapts to target species. The seal attempts to rejoin its colony, but the gap has widened. The orcas position themselves to prevent reintegration, using their bodies as moving barriers. This is the turning point. Within the group, the seal was buffered by confusion and shared defense. Alone, it becomes a singular signal against open water. The fear is not only imminent death, it is the sudden stripping of communal armor. Ecologically, this tactic exerts profound pressure on prey behavior. Seal colonies choose haul-out sites with proximity to ice or shoreline refuge, balancing feeding grounds against predator exposure. Fish schools alter migration routes to avoid known orca territories. The threat of separation shapes habitat selection, reproductive timing, and group cohesion. Yet the narrative does not end in unilateral dominance. Orcas, despite their apex status, are not immune to ecological constraint. Their cooperative hunts require stable social structures and sufficient prey density. Declines in fish stocks or marine mammal populations can fracture pods, leading to nutritional stress. In polluted waters, bioaccumulation of toxins concentrates within their blubber, compromising immune systems and reproductive success. The predator that isolates others is itself vulnerable to environmental fragmentation. There is also risk embedded within specialization. Pods that focus exclusively on particular prey types may struggle when those prey decline. Cultural knowledge, once advantageous, can become limiting if flexibility is reduced. Separation as a hunting tactic depends on predictable group behavior from prey. When prey adapt, altering movement patterns or utilizing new refuges, the strategy must evolve. Returning to the immediate theater, the seal's movements slow. Its oxygen stores diminish as repeated dives deplete reserves. Orcas surface to breathe in coordinated intervals, conserving energy. They are air-breathing mammals, like their prey, but larger lung capacity and efficient oxygen storage in muscle tissue allow longer dives and sustained pressure. They exploit this advantage, driving the seal into cycles of forced submergence. Eventually, the orcas close in. The final strike may involve ramming, tail slaps to stun, or coordinated bites. The kill is decisive, but it is the preceding isolation that ensured its inevitability. Without separation, the seal might have remained one indistinguishable body within a crowd. Alone, it became a target. The ocean regains its deceptive calm. The remaining seals cluster tighter, adjusting formation, their collective behavior altered by the loss. They will haul out differently tomorrow, perhaps choosing thicker ice or shifting colony position. Orcas, too, adjust routes based on success and resistance. Predator and prey are locked in adaptive dialogue. The deeper reversal lies in the realization that the power of the orca does not stem solely from physical strength, but from social cohesion. A solitary orca would struggle to dislodge a seal from ice or dismantle a large fish school. It is the network that creates dominance. The predator that singles out an individual relies entirely on collective unity within its own kind. Separation works because cooperation precedes it. And in a broader sense, orcas themselves can be isolated. Noise pollution from shipping interferes with echolocation and communication, fragmenting pods acoustically. When calls are masked by anthropogenic sound, coordination falters. The hunter that depends on synchronized movement becomes disoriented in a sea filled with mechanical roar. Still, within polar waters where ice drifts and silence reigns, the drama repeats. A colony gathers. A pod approaches. The first disruption is subtle, then catastrophic. The arithmetic of safety fractures. One individual drifts just slightly beyond the protective edge. In that instant, everything changes. The seal is no longer part of a crowd. It is a single heartbeat in open water. Orcas adjust formation, narrowing the corridor of escape, patient and precise. The ocean, vast and indifferent, offers no shelter when the geometry of numbers dissolves. And as the black and white forms rise once more, carving arcs against the grey surface, the lesson reverberates through the ecosystem. Protection is collective, and the moment it breaks, survival becomes solitary. The shell does not crack slowly. It detonates. A crab shifts beneath a ledge, antennae probing the water for chemical traces of food, claws half raised in habitual caution. There is no shadow approaching, no current change, no prolonged tension that might signal danger. The water is still. Then a blur of color flashes from a crevice, and before the crab's neural circuitry can translate stimulus into movement, the world fractures in a burst of cavitation bubbles and shattered calcium. The mantis shrimp does not chase. It does not stalk across open sand with drawn-out menace. It waits inside a burrow carved into reef rock or sediment, forelimbs folded like loaded springs. Its raptorial appendages, modified into hammer-like clubs or spear-like blades depending on species, are held under tension by a latch mechanism powered by elastic energy stored in specialized cuticular structures. The predator is not poised for gradual escalation. It is coiled physics. The crab inches closer to the burrow entrance, unaware that proximity is the only requirement for catastrophe. Mantis shrimp possess some of the most complex visual systems in the animal kingdom, with eyes capable of detecting polarized light and a wide range of wavelengths. Yet this extraordinary perception is not deployed for pursuit across distance. It is used to gauge strike geometry with surgical precision at close range. The predator calculates angle and timing within a confined field measured in centimeters. When the latch releases, the club accelerates with astonishing velocity, reaching speeds that generate forces sufficient to fracture mollusk shells and crustacean exoskeletons. The strike is so rapid that it creates cavitation in the surrounding water, forming vapor bubbles that collapse with additional shock waves. The crab does not experience a sequence of threat, impact, and pain. It experiences an instantaneous collapse of structure. This is not merely a mechanical blow. It is a biochemical and neurological event compressed into microseconds. The mantis shrimp's strike outpaces the prey's startle reflex, a neural pathway evolved to trigger rapid escape in response to sudden stimuli. The latency inherent in synaptic transmission, though measured in milliseconds, is too slow. By the time ion channels open and muscles receive the signal to contract, the club has already connected, and the exoskeleton has already failed. The terror here lies in temporal compression. There is no escalating arc of fear, no sprint through narrowing corridors. The moment of contact is indistinguishable from the end. Mantis shrimp embody a paradox of fragility and force. Their bodies are relatively small, often concealed within narrow burrows that limit mobility. They cannot pursue prey across open terrain with endurance. Instead, evolution has invested in a latch-mediated spring mechanism that converts slow muscular contraction into explosive release. This mechanism exemplifies a principle known as power amplification, where energy stored over time is unleashed in a fraction of that duration. The predator trades stamina for instantaneous dominance within reach. The crab's shell, composed of chitin reinforced with calcium carbonate, is designed to withstand steady pressure and minor impacts. It is not optimized for high-velocity shock delivered at a precise angle. The mantis shrimp's club is structured with a layered composition that dissipates stress, preventing self-damage during repeated strikes. Specialized regions within the club absorb and redistribute force, allowing the predator to deliver blow after blow without structural failure. In the aftermath, fragments drift through the water column. The mantis shrimp retreats slightly, then advances to consume the incapacitated prey. Feeding occurs methodically, but the decisive event has already passed. The burrow returns to stillness, its occupant resetting the latch for the next encounter. Ecologically, mantis shrimp exert selective pressure on hard-shelled invertebrates, influencing population dynamics of crabs, snails, and bivalves within reef systems. Their presence shapes the distribution of prey species, which may avoid burrow-dense substrates or alter foraging patterns to minimize exposure. In this way, the instantaneous strike reverberates outward into behavioral adaptations across the benthic community. Yet the narrative does not remain one of unilateral invincibility. Mantis shrimp are themselves vulnerable to larger predators such as fish and octopuses. Outside the protective radius of their burrows, their compact bodies offer limited defense. Their reliance on proximity means that open water exposure carries significant risk. The same specialization that grants them unmatched striking speed confines them to territories measured in meters rather than miles. Furthermore, their burrows represent both fortress and trap. If sediment shifts or coral rubble collapses, escape routes may be blocked. In heavily disturbed habitats, burrow stability declines, increasing mortality risk. The predator of microseconds depends on geological patience. There is also an unexpected dimension to their visual sophistication. While mantis shrimp possess extraordinary photoreceptor diversity, research suggests that their neural processing may categorize colors differently than human perception, prioritizing rapid discrimination over detailed comparison. Their eyes are optimized for speed of recognition rather than contemplative analysis. Vision serves the strike, not aesthetic appreciation. The reversal deepens when considering that the mantis shrimp's apparent ferocity masks a life defined by territorial solitude. Many species are monogamous, maintaining long-term pair bonds within shared burrows. The lethal club is wielded not only against prey, but occasionally in ritualized combat with rivals. Yet these confrontations are governed by signaling and assessment, minimizing fatal outcomes. Violence is precise, not indiscriminate. Returning to the moment of impact, the defining feature is absence of transition. The crab does not sense encroaching danger over distance. It crosses an invisible threshold and is erased by physics. The water's surface remains undisturbed. No predator arcs dramatically through the blue. The event is confined to a space barely larger than the predator's own body. In a reef ecosystem, often defined by prolonged chases and coordinated hunts, the mantis shrimp represents a different axis of fear. It compresses cause and consequence into a singular flash. The environment does not gradually constrict or surround. It simply converts from neutral to lethal without perceptible warning. The burrow mouth, dark and unassuming, resumes its role as architectural feature rather than threat. Small fish and crustaceans resume their foraging, navigating the mosaic of rock and sand. Yet within that narrow cavity lies a mechanism capable of delivering force comparable to a projectile. The mantis shrimp waits, appendages folded, energy accumulating slowly within elastic structures. Muscles contract without visible movement, storing potential. Time stretches in stillness until proximity aligns with calculation. Then, in a fraction beyond perception, stored energy becomes impact. And for the prey, the moment of contact is indistinguishable from the end. The seal never sees the geometry forming beneath it. At the surface, the world feels open, almost buoyant with safety. Light fractures into silver ribbons, scattering across its whiskered face as it exhales in a quiet plume and rolls back into the water. Above, the sky is a pale dome. Below, the ocean collapses into ink. The seal's muscles move with easy confidence, its foreflippers slicing cleanly through the upper layer where sunlight still penetrates. But beneath that threshold, where blue fades into a pressure-darkened void, a different calculus is unfolding. A predator is not rushing. It is not chasing. It is calculating. The seal's silhouette has already been measured, its trajectory plotted against the physics of buoyancy and refraction. The calm surface is an illusion of ignorance. The hunt has begun long before the seal feels anything at all. Seals evolved for the boundary layer, that luminous interface between air and sea, where breath can be taken and light can be read. Their large, forward-facing eyes are exquisitely adapted to gather faint illumination, their retinas packed with rods to enhance sensitivity in dim water. Their vibrissae, those thick, tactile whiskers, can detect the minute hydrodynamic trails left by fish, passing turbulence patterns with neurological precision. Every anatomical feature suggests awareness. Yet the architecture of vision in open water is brutally asymmetric. From above, the ocean surface reflects and refracts, scattering incoming light into unpredictable angles. From below, however, the surface becomes a luminous ceiling. Any creature swimming near it is rendered as a high-contrast silhouette against brightness. The predator sees a shadow, crisp and distinct. The seal sees only darkness. This imbalance is not incidental. It is a fundamental optical trap. Water absorbs longer wavelengths first, swallowing reds and oranges as depth increases, leaving a narrowing spectrum of blue. As light diminishes, shapes flatten into silhouettes. A seal cruising within the top few meters becomes a glowing cutout against the sunlit lid of the sea. Beneath that lid, vision sharpens toward contrast detection rather than detail recognition. The predator does not need color or nuance. It needs outline and motion, and the seal provides both. But the terror is not in the strike. It is in the waiting. Predators that attack from below, particularly large lamnid sharks and transient orcas, do not rely solely on brute acceleration. They rely on sensory layering. Electroreceptors embedded in their snouts detect the faint electrical fields generated by muscle contractions. Lateral line systems register pressure waves as the seal's flippers beat rhythmically. Olfactory tissues analyze microscopic traces of scent dissolved in water, carried across currents invisible to the seal itself. By the time the predator ascends, the seal has already been mapped in multiple sensory dimensions. The attack is merely the final expression of a process that began minutes earlier. Here, the narrative seems simple. The seal is prey, vulnerable at the surface, betrayed by physics and light. But that assumption fractures under scrutiny. For the seal's apparent exposure is also a calculated trade-off, shaped by metabolic constraints and oxygen economics. Diving deep into darkness would not eliminate risk. It would introduce a different predator set, different hazards. Depth increases pressure, compressing air spaces and accelerating oxygen depletion. Seals manage breath with remarkable physiological control, shunting blood flow to essential organs, slowing heart rate in what is known as bradycardia. Yet extended deep dives demand recovery time at the surface. The boundary layer is not recklessness, it is necessity. And necessity breeds adaptation. The seal's body is built for sudden vertical displacement. Its spine flexes with explosive force, its rear flippers generating thrust sufficient to alter trajectory in a fraction of a second. Beneath its skin lies a thick layer of blubber, often mischaracterized as mere insulation. In truth, this adipose tissue is both thermal armor and energy reservoir, sustaining rapid bursts of anaerobic movement when oxygen runs low. When the strike comes from below, survival depends not on outswimming the predator in a marathon, but on outmaneuvering it in an instant. Predators attacking from depth face a physiological paradox. To reach the surface quickly, they must accelerate upward, converting stored muscular energy into vertical velocity. But as they ascend, buoyancy increases. The pressure that once compressed gases within their bodies relaxes. Their own silhouette becomes visible against the bright ceiling. They are committed to a trajectory that limits last-moment corrections. If they miscalculate by even a body length, the opportunity collapses. The seal, sensing the faintest distortion in water pressure or detecting a sudden shift in light pattern, can twist laterally, disrupting the predator's aim. The ocean's calm surface conceals not just danger, but mutual vulnerability. There are documented moments when seals have exploited this dynamic with astonishing precision. Rather than fleeing horizontally, some perform abrupt corkscrew dives, plunging downward at sharp angles to break the predator's line of ascent. Others surge toward the very predator approaching them, collapsing the distance before acceleration peaks, forcing a misfire. What appears to be panic is often neuromuscular choreography refined over evolutionary time. Neural pathways linking sensory input to motor response are honed to minimize delay. In these fractions of seconds, survival hinges on synaptic speed. Yet even this portrayal understates the ecological complexity beneath the scene. The presence of apex predators influences seal behavior long before individual encounters occur. This is the architecture of the trophic cascade. In regions where large sharks or orcas patrol frequently, seals alter haul-out patterns, shift feeding times, and modify travel corridors. They avoid predictable routes. They cluster near kelp forests or complex substrates that disrupt vertical attack paths. The fear itself reshapes movement across entire coastal systems. Kelp beds grow denser in areas where seals reduce grazing pressure on herbivorous fish. The unseen predator does not merely kill. It reorganizes the ecosystem through psychological pressure. And here lies the deeper reversal. The terror of being watched from below is not solely an affliction of the seal. The seal too watches. Its large eyes scan the dimness, interpreting gradients of shadow that most terrestrial mammals could never decipher. Its whiskers extend outward, splayed like antennae, reading disturbances in the fluid medium. What seems like open vulnerability is also hyper-awareness. The surface is not a place of ignorance. It is a sensor platform. In polar waters, where ice flows fracture light into chaotic geometries, this interplay becomes even more intricate. Seals resting near breathing holes in sea ice are acutely aware that predators may wait beneath those very apertures. The hole is both lifeline and trap. Orcas have been observed coordinating to generate waves that dislodge seals from ice platforms, transforming solidity into instability. But seals respond with behavioral plasticity. They distribute themselves unpredictably across flows, minimizing the chance of mass displacement. They maintain sentinel vigilance even while appearing to sleep. One hemisphere of the brain can enter rest while the other remains partially alert, a neurological compromise between recovery and awareness. The ocean looks calm because surface tension smooths its expression. Beneath that veneer, gradients of temperature and salinity form invisible boundaries, known as thermoclines and haloclines. Sound travels differently across these layers, bending and refracting in ways that can mask or amplify movement. A predator rising from cold, dense water into warmer strata may briefly lose acoustic clarity. A seal passing through these gradients might distort its own acoustic signature. The battlefield is not two-dimensional. It is stratified, layered, dynamic. When a breach finally occurs, when a predator erupts upward in a plume of white water and torn spray, the spectacle captures attention. But by that point, the story is almost over. The real drama unfolded in darkness, the silent triangulation, the subtle adjustments in depth, the metabolic calculations balancing oxygen reserves against opportunity. The seal's fear, if it can be called fear, is embedded not in conscious anticipation, but in inherited reflex. Generations of selection pressure have encoded caution into muscle memory. To the human observer floating above, the sea appears tranquil. Sunlight dances. Ripples shimmer. The seal glides, its rounded head breaking the surface in rhythmic intervals. Nothing seems amiss. Yet the predator's perspective inverts that tranquility into opportunity. The luminous ceiling outlines prey with mathematical clarity. The boundary between light and dark becomes a weaponized horizon. And still, the narrative refuses to settle into a simple hierarchy of victim and executioner. For apex predators, too, operate within constraints. Missed strikes expend immense energy. Repeated failures risk starvation. Juvenile sharks and inexperienced orcas must learn the geometry of ascent through trial, often enduring painful miscalculations. In this interplay, the seal is not passive. It is a participant in an evolutionary arms race, measured not merely in teeth and speed, but in perception and timing. The true terror of being watched from below is therefore not ignorance. It is asymmetry. It is the realization that in certain layers of the world, physics favors one perspective over another. The seal swims through brightness, unaware of the precise location of its observer, yet exquisitely attuned to the possibility. The predator waits in shadow, confident in contrast but vulnerable to misjudgment. Both are bound by the same medium, the same laws of light absorption and pressure, the same metabolic arithmetic. As evening approaches and the angle of the sun lowers, the luminous ceiling dims. Contrast softens. The seal's silhouette blurs. The advantage shifts again. Twilight compresses visibility for predator and prey alike, redistributing risk across the water column. What seemed like certain vulnerability at midday dissolves into ambiguity. The ocean does not belong permanently to the watcher or the watched. It belongs to whoever understands its shifting optics at any given moment. And so the seal continues to swim near the surface, not because it is careless, but because life demands negotiation with danger. Every breath taken in open water is an act of calculated exposure. Beneath the mirrored skin of the sea, something may already be tracking movement, measuring distance, waiting for alignment. The calm above is never a guarantee. It is merely the final deceptive layer of a world where light itself can betray you. The first penguin stands at the edge. wind pressing its feathers flat against a body engineered for water yet stranded on stone. Beneath the ice shelf, the sea looks calm, a sheet of fractured light trembling against the horizon. But the hesitation is not theatrical. It is neurological. In that narrow pause before the leap, an entire evolutionary calculation unfolds inside a skull no larger than a clenched fist. The bird cannot see what waits below. The water is a mirror from above and a void from within. Once it jumps, buoyancy will seize control, drag will dictate trajectory, and gravity will surrender authority to fluid mechanics. There will be no mid-air reconsideration. The leap is commitment, and commitment in this ecosystem is the difference between feeding and becoming food. Penguins are masters of two incompatible worlds. On land, they are upright, slow, and exposed. In water, they are torpedoes, wings reshaped into hydrofoils, capable of generating lift and thrust simultaneously. Their bones are denser than those of flying birds, reducing buoyancy so that dives are not wasted energy battles against flotation. Muscles anchored along a streamlined sternum drive, strokes that convert metabolic fuel into forward momentum with startling efficiency. But the transition point, the instant of entry, is a blind threshold. Light striking the ocean surface refracts unpredictably, scattering into angles that distort depth perception. From above, the water conceals its interior. From below, anything crossing that luminous membrane is outlined in stark silhouette. This asymmetry shapes behavior with ruthless precision. Penguins do not tumble casually into the sea. They gather, shuffle, wait. Individuals cluster at the edge, their dark backs absorbing solar radiation while their white bellies flash against the snow. That coloration, known as counter-shading, is not aesthetic. It is optical camouflage. From below, the white belly blends with surface brightness. From above, the dark dorsal side dissolves into deeper water. But camouflage is only effective after immersion. Before that, the penguin must decide. The hesitation is often misinterpreted as timidity. In truth, it is risk distribution. By crowding together at the edge, penguins reduce individual predation probability through dilution effect. If a leopard seal patrols beneath the ice, it cannot strike them all. Yet someone must jump first. The initial diver breaks the informational barrier, triggering a cascade of movement. This phenomenon is not simple panic. It is social facilitation, a neurological response where one individual's action reduces the perceived cost of risk for others. The group becomes a probabilistic shield. Below the surface, the physics shifts abruptly. Air trapped in feathers compresses under pressure, reducing insulation, but also minimizing buoyant drag. Penguins manage this with remarkable control, preening to trap just enough air for thermal buffering while avoiding excess flotation that would waste energy during descent. Their blood chemistry supports extended dives through elevated myoglobin concentrations in muscle tissue, storing oxygen for underwater propulsion. Yet these adaptations cannot erase uncertainty. The water column is three-dimensional, layered with gradients of temperature and salinity that bend sound and light. Visibility may collapse within meters. The predator does not need to be visible, it needs to be present. Leopard seals and orcas exploit this threshold ruthlessly. They patrol beneath ice edges, scanning upward silhouettes for the unmistakable shape of a descending penguin. From below, the penguin's streamlined form is highlighted against a pale ceiling. The predator's retina, tuned for contrast rather than detail, interprets motion as opportunity. When acceleration begins, it is vertical, driven by powerful axial musculature. The attack is not chaotic. It is geometry solved in motion. But here lies the narrative reversal. The penguin's leap is not blind surrender. It is a maneuver shaped by hydrodynamics that the predator must respect. Penguins enter the water at angles calculated to maximize forward velocity while minimizing splash signature. Some species launch themselves in porpoising arcs, breaking the surface repeatedly to breathe without losing speed. This behavior reduces time spent in the vulnerable boundary layer where predators strike from below. What appears to be frantic hopping across water is actually energy optimization, reducing drag by alternating between fluid and air phases. The leap into uncertainty is followed by mastery of it. The fear is not the attack, it is the invisibility. In polar regions, particulate matter suspended in water scatters light, creating a visual fog that obscures distance. Sound travels faster in water than in air, but it also refracts across thermoclines, bending away from predictable paths. A penguin cannot rely solely on sight. Its lateral line equivalent, sensitive feather follicles and mechanoreceptors, detect subtle vibrations. The brain integrates these signals into split-second directional adjustments. Neural pathways connecting visual cortex and motor output are streamlined for speed. Reaction time is survival, yet predators face constraints of their own. Rapid upward acceleration demands immense energy expenditure. A missed strike costs calories in an environment where prey availability fluctuates seasonally. Penguins time their entry strategically, often during periods when predator density is lower or when group size increases dilution advantage. In breeding seasons, synchronized departures from colonies overwhelm individual predators with too many targets at once. This is not chaos. It is emergent coordination driven by selective pressure. The leap also represents a metabolic gamble. On land, penguins burn energy maintaining body temperature against katabatic winds that scour Antarctic coastlines. In water, despite the cold, heat loss can be slower due to insulation and hydrodynamic efficiency. Feeding requires immersion. Fish and krill form dense shoals beneath ice, their distribution influenced by nutrient upwelling and seasonal phytoplankton blooms. Penguins must dive to sustain themselves and their chicks. Avoiding the water entirely is not an option. Hesitation is not avoidance, it is calculation. Consider the sensory paradox at play. From the penguin's vantage, the ocean surface is opaque. From beneath, it is translucent. This inversion of perspective defines predator-prey dynamics in marine ecosystems globally. Countershading evolved precisely because of this optical structure. Penguins, seals, and countless fish species share this adaptation, a testament to the persistent geometry of light underwater. The leap becomes a ritual acknowledgement of physics, and then, once submerged, the penguin transforms. Wings that once propelled ancestors through air now slice water with precision. Stroke cycles generate lift on both downstroke and upstroke, unlike most birds. The skeletal architecture of the flipper resists bending under pressure, maintaining hydrofoil shape even at depth. Penguins can reach impressive velocities, outpacing many fish and evading some predators through agility alone. The vulnerability of the jump is counterbalanced by dominance in motion. There are moments when predators miscalculate. A leopard seal lunges, only to grasp a swirl of bubbles as the penguin veers laterally with explosive force. Orcas may herd penguins against ice, yet individuals slip through turbulence in unpredictable trajectories. The same water that conceals predators also disrupts their precision. Currents swirl around icebergs, creating eddies that bend pursuit paths. The ocean is not a stable battlefield. It is a dynamic fluid medium. Still, uncertainty remains the defining emotion of the edge. Evolution cannot eliminate risk. It can only manage it. Penguins standing on ice are acutely aware, through instinct, through inherited neural circuitry, that the water is both larder and abyss. Their pause is a silent negotiation with the unknown. Once they lean forward, gravity takes command. The body arcs, feathers slicing wind, and then the surface breaks with a muted crack as fluid replaces air. From that moment, retreat is no longer immediate. Buoyancy patterns shift. The bird must commit to depth or speed. There is no hovering between states. The threshold has been crossed. This is the essence of the leap, an irreversible transition between worlds governed by different physical laws. Air allows hesitation. Water demands momentum. As colonies return from feeding trips, bellies heavy with fish, the cycle repeats in reverse. Penguins erupt from the sea onto ice, evading predators in the final meter through ballistic launches that convert underwater velocity into airborne escape. The same physics that endangered them becomes their shield. Momentum becomes armor. The ecological implications ripple outward. Penguins regulate krill populations, influencing phytoplankton dynamics through trophic cascades. Their dives redistribute nutrients vertically, excreting waste that fertilizes coastal ecosystems. Predators targeting penguins, in turn, shape penguin distribution, altering grazing pressure across marine food webs. The leap into uncertainty is not isolated drama. It is a structural component of polar ecology. And so the scene returns to the edge. A line of penguins stands poised against wind and glare. Beneath them, the sea remains inscrutable, concealing currents, predators, and opportunity alike. The hesitation stretches, not as weakness but as evidence of a mind attuned to risk. When one finally tips forward, the colony follows in a cascade of black and white arcs, surrendering to water that may conceal death, yet guarantee survival. The ocean never reveals what waits below. That opacity is constant. But the leap, repeated generation after generation, embodies a profound biological truth. Life persists not by eliminating uncertainty, but by mastering it. The water fractures into motion before the squid understands why. One instant it is suspended in the pelagic blue, chromatophores pulsing faintly across its mantle in slow waves of communication. And the next, the geometry of space collapses inward. A shadow crosses from above, another streaks from the flank, and a pressure ripple surges from below. There is no reef to anchor against, no seabed to press into, no forest of kelp to dissolve within. Open water offers speed but denies shelter. The squid's nervous system ignites, firing impulses down a ring-shaped brain wrapped around the esophagus, routing signals to mantle muscles primed for escape. Jet propulsion erupts in a violent pulse, siphon angled backward, water expelled with explosive force. Velocity spikes, but the sea around it is no longer empty. It is closing. Squid are built for acceleration. Their muscular mantle acts as a living pump, drawing water into a cavity and ejecting it through a narrow funnel, converting muscular contraction into thrust through Newtonian reaction. Circular and radial muscle fibers coordinate to regulate intake and expulsion, producing bursts of speed that can exceed most fish in short sprints. The body is streamlined, fins stabilizing direction, arms and tentacles trailing with aerodynamic discipline. Yet propulsion comes at a cost. Jetting is metabolically expensive, driven by anaerobic muscle fibers that accumulate lactate rapidly. A squid can outrun a single predator, but it cannot outrun physics. In solitary pursuit, escape is choreography. The squid senses an approaching predator through stetocysts that detect orientation and acceleration, through mechanoreceptors embedded in its skin that register minute changes in water pressure, through eyes that rival vertebrate optics in resolution. It shifts hue instantly, chromatophores expanding to darken its mantle, iridophores reflecting ambient light to distort its outline. A cloud of ink erupts from a specialized sac near the gut, forming a decoy mass known as a pseudomorph. The predator lunges at the ink silhouette while the squid vanishes in a burst of jetting velocity. In these one-on-one duels, survival often favors the cephalopod's agility. But when predators converge from multiple vectors, the calculus mutates into chaos. Schooling fish close in from one direction, driving the squid upward. A dolphin pod arcs from the periphery, coordinating through echolocation pulses that map three-dimensional space with acoustic precision. Beneath, a predatory tuna slices upward, its red muscle tissue sustaining prolonged pursuit. The open water becomes a sphere of threat. Every jet burst drains oxygen. Every maneuver narrows remaining options. Unlike fish, squid lack rigid skeletal support. Their hydrostatic bodies rely on internal pressure to maintain shape. Sustained high-speed movement risks destabilizing that delicate balance. Confusion spreads not as emotion, but as physiological overload. The squid's neural architecture is decentralized. Large ganglia extend into each arm, allowing semi-autonomous movement. This design permits extraordinary flexibility and rapid reflex arcs, but under multi-directional assault, it can produce conflicting motor commands. One arm signals for lateral evasion, while the mantle contracts for vertical thrust. Ink deployment may obscure one predator while revealing the squid's position to another through chemical cues. Cephalopod ink contains melanin and mucus, forming a dense cloud, but it also carries chemical signals that may alert predators attuned to scent gradients. What begins as defense becomes a beacon. Energy reserves deplete rapidly. Squid lack the sustained aerobic endurance of tuna or dolphins. Their hemocyanin-based blood, relying on copper rather than iron for oxygen transport, is efficient in cold, oxygen-rich waters, but less capable under intense exertion. As lactate accumulates in mantle muscles, contraction efficiency drops. Jet propulsion becomes erratic. Speed falters. Panic, if it can be called that, is the visible manifestation of metabolic collapse. The surrounding predators exploit this spiral. Dolphins herd squid into tight clusters, compressing escape space deliberately. Their intelligence is not abstract. It is ecological, shaped by cooperative hunting strategies refined over generations. By driving prey toward the surface, they eliminate vertical escape routes. Tuna accelerate from depth, using counter-shaded bodies to remain invisible until the final surge. Each predator species imposes a different constraint, and together they create a closing lattice of motion. At first glance, this scenario seems terminal. The squid's celebrated speed becomes irrelevant when directionality is compromised. Open water, once freedom, is now exposure. Yet within this vortex of pursuit lies a subtler adaptation rarely acknowledged. Many squid species do not face such assaults alone. Beneath the surface of apparent individuality lies a phenomenon known as dynamic schooling. While squid lack the rigid cohesion of fish schools, they are capable of forming synchronized aggregations that shift shape and density in response to threat. Chromatophore patterns flash in coordinated waves, transmitting signals across bodies in milliseconds. These visual cues are more than display. They are information exchange. When predators approach from multiple directions, individual squid may align, creating a shifting mass that confuses targeting algorithms in predator brains. This is the reversal. The same nervous system that fragments under solitary panic becomes a collective amplifier in groups. Movement patterns synchronize, generating a flickering wall of bodies whose reflective iridophores scatter light chaotically. Predators relying on visual locking struggle to isolate a single target within the swarm. Dolphins must recalibrate sonar echoes distorted by overlapping bodies. Tuna may overshoot, slicing through empty water as the group shifts like a living smoke cloud. Ink, too, transforms under collective use. Multiple individuals releasing ink simultaneously create a volumetric fog, not merely a decoy blob, but a broad opacity field. Within this temporary darkness, squid reverse direction, some even swimming toward predators momentarily to exploit blind zones in pursuit paths. What appears as panic is tactical entropy, a deliberate increase in environmental noise that destabilizes predator coordination. But this strategy carries costs. Grouping increases competition for food and may attract larger predators capable of penetrating confusion through sheer force. Energy expenditure multiplies as each individual jets to maintain position within the dynamic mass. Metabolic strain remains acute. The sea does not grant unlimited reprieve. As oxygen debt deepens, some squid resort to a final adaptation. Bioluminescence. Photophores embedded in skin emit controlled flashes, mimicking downwelling light from above in a strategy known as counter-illumination. By matching brightness to ambient conditions, the squid erases its silhouette when viewed from below. In multi-directional assaults, this camouflage can disrupt attacks from predators relying on contrast detection. Yet bioluminescence requires precise neural control and energy investment. Overuse may reveal rather than conceal. The open ocean is not empty space. It is a fluid arena governed by thermoclines, current shear, and pressure gradients that alter sound and light transmission. Predators navigating this arena exploit physical features invisible to prey. Dolphins may drive squid toward convergence zones where currents meet, compressing escape trajectories. Tuna utilize thermal layers that enhance muscle efficiency. The squid must interpret these invisible structures while under duress. And still, sometimes survival emerges from collapse. When energy drains to near failure, some squid abandon propulsion and sink, reducing movement signature abruptly. Predators expecting continued acceleration overshoot, momentum carrying them beyond immediate reach. In the brief silence that follows, the squid regains control, mantle muscles contracting minimally to restore orientation. What appears to be surrender is strategic stillness. The hydrostatic body, once destabilized by frantic jetting, recenters under gravity's subtle pull. In a medium where movement attracts attention, immobility can be camouflage. The ecological implications ripple outward. Squid occupy a central trophic position, converting zooplankton and small fish into biomass that fuels higher predators. Their vulnerability sustains dolphin pods and tuna migrations, which in turn regulate fish populations and nutrient cycling across ocean basins. Multi-directional predation events are not anomalies. They are structural forces shaping pelagic ecosystems. The panic spiral of a single squid reflects the broader thermodynamic reality of open water life. Energy flows upward through risk. Open water promises freedom but demands vigilance. Speed offers escape but consumes life. When predators approach from multiple directions, the squid confronts the limits of its design. And yet within those limits lies astonishing adaptability. Collective signaling, volumetric camouflage, metabolic recalibration. Confusion may rise, energy may drain, but the story does not end in inevitability. It unfolds in fluid negotiation between chaos and control. The sea never empties entirely. It waits, layered and immense, ready to close again. The surge hits sideways, not hard enough to kill, just precise enough to unbalance. One instant the crab is anchored against rock, legs splayed wide, claws lifted in defensive geometry, its carapace absorbing the brunt of a breaking wave. The next instant, gravity rotates. The world inverts. Its armored dome that once faced upward now presses helplessly against stone, and the pale, vulnerable underside opens to the sky like an unlocked door. The crab's strength was never in speed, never in size, but in orientation. The shell protects only when the body is correctly aligned with the world. Flip that alignment, and the architecture collapses. A crab's body is a study in defensive engineering. The dorsal carapace is a fused shield of calcified exoskeleton, hardened with calcium carbonate deposited in layers that resist compression and puncture. The front is guarded by chelae, claws that combine crushing force with sensory acuity, detecting vibrations through mechanoreceptors embedded in chitin. The legs extend outward in a wide stance, allowing lateral movement that minimizes exposure of softer abdominal tissue. Evolution did not make crabs symmetrical in defense. It made them directionally armored. But the underside tells a different story. Beneath the shell lies a flexible abdomen folded tightly against the thorax, thinner exoskeleton protecting gill chambers that require constant water flow for respiration. This ventral surface is built for efficiency, not battle. It is the gateway to the animal's physiology. Gills exchanging dissolved oxygen, nerve cords transmitting signals, reproductive organs secured within a chamber never meant to face the open world. The moment a crab is flipped, these hidden structures become visible and accessible. The defense ceases to function. Flipping is rarely dramatic. It may be the unintended consequence of a surge, a misjudged step on algae-slick rock, or the probing beak of a shorebird applying leverage to the edge of the shell. Predators understand the geometry instinctively. Gulls do not attempt to pierce the armored top. They seize and twist. Sea otters, dexterous and patient, manipulate crabs in forepaws, rotating them until gravity assists the disassembly. Even rival crabs exploit the vulnerability during territorial contests, grappling not to crush, but to overturn. Once inverted, control becomes a frantic recalibration of biomechanics. The crab's legs, designed for lateral propulsion against substrate, now scrape uselessly against air or smooth rock. Without firm contact, leverage disappears. The joints, powered by muscles that contract against internal apodemes, struggle to generate torque sufficient to right the body. Every movement expends energy, and metabolic reserves are finite. The exoskeleton does not bend to compensate. It is rigid by design. Rigidity grants protection when upright, but denies flexibility when compromised. Respiration becomes compromised as well. Gills, normally bathed in water flowing through branchial chambers, may dry if exposure persists. Oxygen exchange falters. Hemolymph circulation, driven by a dorsal heart pumping through open sinuses, cannot compensate for the lack of moisture. What was once a sealed fortress now becomes a suffocating cage. And yet the transformation from protected to exposed is not merely physical, it is ecological. On rocky shores, crabs function as regulators of algae and detritus, grazing on biofilms that would otherwise overgrow tidal zones. Their presence influences the distribution of mussels and barnacles, shaping community composition in intertidal ecosystems. When a crab is flipped and consumed, energy transfers upward to birds or mammals, altering nutrient flow across trophic levels. A single misstep becomes a node in a larger web of exchange. Still, the vulnerability of inversion seems absolute. The crab, upside down, appears doomed. Its legs thrash, claws open and close reflexively, but gravity remains relentless. Predators close in. The shell that once deflected force now traps the body in exposure. This is where the narrative reverses. Many crab species possess specialized righting mechanisms evolved precisely because flipping is inevitable in dynamic environments. The same wide legs that provide lateral stability can function as levers when applied strategically. By arching the abdomen and anchoring one claw against substrate, some crabs generate rotational force, exploiting their own mass distribution to tip back onto their feet. The process is not elegant, but it is effective. Neural circuits embedded in the ventral nerve cord coordinate a sequence of contractions that maximize torque under minimal contact. What appears as frantic flailing is often patterned movement encoded by selection pressure. Certain species go further. Decorator crabs, cloaked in sponges and algae attached deliberately to their shells, add irregular mass distribution that can aid in destabilizing inverted positions. Hermit crabs, inhabiting borrowed shells, use the curvature of their mobile homes as rolling surfaces, allowing them to rock back upright. Even the rigid architecture of the exoskeleton hides microflexibility at joints that permit subtle adjustments in leverage. The vulnerability of inversion also exposes a physiological strength, tolerance for transient hypoxia. Crabs routinely endure fluctuating oxygen levels in tidal pools where respiration becomes limited during low tide. Their hemocyanin exhibits variable oxygen affinity depending on temperature and pH, allowing survival through brief periods of respiratory stress. Thus, even when gills are partially compromised, the animal may endure long enough to regain orientation. Predators, too, face constraints. A gull attempting to extract soft tissue must contend with sharp claws that remain dangerous even when inverted. Sea otters require time and stable surfaces to exploit a flipped crab fully. In turbulent surf, maintaining control over prey is difficult. The intertidal zone is not static. Waves continue to break, currents shift, and a crab overturned by one surge may be righted by the next. Environmental volatility can interrupt predation sequences. What seems like helplessness is therefore conditional, not absolute. The structural asymmetry of the crab's body, hard above, soft below, reflects evolutionary trade-offs. Allocating equal armor across all surfaces would impose prohibitive energetic costs during molting, when crabs shed their exoskeletons to grow. Molting itself represents another period of profound vulnerability, when the new shell remains soft and pliable until mineralization completes. During that window, even upright crabs are defenseless. Yet molting is essential for growth and reproduction. Risk is woven into life history. Inversion mirrors molting in its exposure of hidden anatomy. Both events strip away the illusion of invincibility provided by the shell. Both reveal that defense is contextual, dependent on timing and orientation. The crab's survival hinges not on constant strength, but on rapid recovery. Consider also the ecological choreography between crabs and their predators. Shorebirds learn to time foraging with tidal rhythms, targeting crabs when waves increase flipping probability. Otters select rocky platforms that facilitate manipulation. Predatory fish in shallow waters exploit moments when crabs drift off balance. Each predator species has evolved behavioral adaptations, specifically tuned to exploit inversion events. In turn, crabs evolve refinements in grip strength, substrate selection, and reflex speed. Energy expenditure during righting is significant. Repeated flipping events can deplete glycogen stores in muscle tissue, leaving the crab weakened even if it survives immediate attack. Thus, maintaining secure footing becomes a priority behavior. Many species select microhabitats that reduce flipping risk: crevices, undercut rocks, or sediment burrows that anchor the body against hydrodynamic force. Burrowing species use specialized appendages to dig rapidly, submerging themselves until only eye stalks protrude. In such positions, inversion becomes nearly impossible without substantial disturbance. And yet, no environment eliminates risk entirely. A sudden shift in current, an unexpected collision with debris, or an aggressive rival can undo stability in an instant. The moment of losing footing is not rare. It is inevitable across a lifetime shaped by tides. As the crab strains against gravity, legs scraping rock in deliberate sequence, the transformation from exposed target back to armored defender unfolds in seconds that feel geological. A successful rotation re-establishes orientation. The dorsal carapace faces upward once more, claws reassert dominance, and the illusion of invulnerability returns. But the memory of inversion persists in muscle fatigue and neural recalibration. The animal adjusts its stance subtly, selecting firmer ground, bracing against future surges. Survival is iterative. The shore returns to apparent normalcy. Waves break. Algae sway. The crab resumes grazing, shell gleaming under shifting light. Yet beneath that hardened exterior lies the knowledge encoded in tissue and reflex. Protection is not permanent. It depends entirely on position. In a world governed by fluid force and opportunistic predators, a single moment of imbalance can rewrite fate. The crab's defense is real, formidable even, but it is conditional. Orientation is armor. Lose it, and exposure follows. And still, against odds shaped by gravity and hunger, the crab stands upright once more, proof that vulnerability and resilience are often separated by the smallest turn of the body. The grip lands before the prey understands it has been touched. One instant a crab is picking across the sand, antennae tasting the current for traces of food, and the next the water itself seems to seize it. Arms erupt from a crevice with silent precision, not striking like a predator in open pursuit, but unfolding like a trap that has already decided the outcome. The octopus does not lunge blindly. It envelops. In a fraction of a second, 8 muscular limbs flow over shell and claw, sliding into crevices, anchoring along joints, mapping every contour of resistance. The fear is not the bite. It is the immediate and total loss of autonomy. Movement ceases to belong to the prey. An octopus arm is not merely a limb. It is a distributed intelligence. Each arm contains a dense network of neurons capable of independent processing, allowing it to probe, taste, and respond without waiting for centralized commands. The suction cups lining the underside are more than passive grips. Each is a muscular hydrostat equipped with sensory cells that detect texture and chemical composition. When a cup presses against surface, circular muscles contract, expelling water and creating negative pressure. The seal is instantaneous. Once engaged, the cup does not simply cling, it locks. Breaking that seal requires force that most prey cannot generate without leverage. Control escalates rapidly because the octopus does not rely on a single anchor point. Hundreds of suction cups coordinate in overlapping patterns, distributing force across the prey's body. A crab's claws may snap, but each snap is met with multiple points of contact that shift and reattach in response. The prey's shell, designed to deflect piercing attacks, offers little defense against compression from all directions. The octopus manipulates limbs into positions that reduce torque potential, neutralizing leverage before the prey can apply it. The octopus's musculature is composed almost entirely of soft tissue, arranged in longitudinal, transverse, and oblique fibers. This architecture permits extraordinary flexibility, allowing arms to bend at any point along their length without skeletal constraints. It also allows force to be applied in complex vectors. When prey attempts to pull away, the octopus tightens selectively, increasing pressure on specific joints while maintaining grip elsewhere. Control becomes dynamic rather than static. The neurological dimension of this encounter is equally decisive. The octopus brain integrates tactile and chemical information in real time, identifying vulnerable points in the prey's anatomy. In crabs, this often means targeting the articulation between carapace segments or the softer membrane near the mouthparts. The beak, concealed at the center of the arm cluster, remains poised. But immobilization precedes penetration. The octopus prioritizes restraint before delivering venom through saliva containing neurotoxins that disrupt neural transmission. Loss of control is not gradual. It is immediate. The prey's motor patterns, evolved to respond to directional threats, fail under omnidirectional constraint. There is no singular attacker to face, no predictable trajectory to evade. Every movement meets resistance. The octopus anticipates recoil, absorbing energy through flexible arms that yield and reassert pressure simultaneously. The prey's nervous system enters overload, signals firing in rapid succession as muscles strain against unyielding suction. This strategy reflects a fundamental ecological truth. In complex substrates, such as coral reefs or rocky seafloors, speed is often less valuable than grip. Octopuses are ambush predators, relying on camouflage and proximity rather than pursuit. Their skin contains chromatophores, iridophores, and leucophores that allow instantaneous color and texture change, blending seamlessly into surroundings. Prey often approaches within reach, unaware that the rock it grazes is a living predator. The attack unfolds within the spatial scale of centimeters rather than meters, yet the apparent helplessness of the prey conceals an ecological reversal. Crabs and fish are not passive victims in evolutionary history. Many species have developed reflexes triggered by tactile stimuli that can disrupt the octopus's hold. Some crabs autotomize limbs, sacrificing a claw to escape, exploiting the octopus's distributed grip by abandoning a trapped appendage. Certain fish secrete mucus that reduces friction, making suction more difficult to maintain. Even the octopus's venom is not universally effective. Prey species exposed to predation pressure may evolve partial resistance, prolonging the struggle. Moreover, the octopus itself operates under metabolic constraints. Its soft body, while flexible, offers little protection against counterattack. A crab's claw, if not immobilized immediately, can inflict significant damage to an arm, and regeneration, though possible, demands energy investment. Each predation event carries risk. The octopus must calibrate force precisely, avoiding injury while securing prey swiftly. The suction cup mechanism, often perceived as infallible, is sensitive to substrate texture and water pressure. In turbulent conditions, maintaining seals becomes more challenging. If prey thrashes violently in strong currents, some cups may detach momentarily. The octopus compensates by redistributing grip, but this requires neural coordination and muscular endurance. Immobilization is not a singular act, but an ongoing negotiation of force. What distinguishes the octopus in this arena is the immediacy of control. Unlike predators that rely on teeth or claws to wound, the octopus dominates space. Its arms form a cage that moves with the prey, collapsing potential escape routes into narrow corridors already occupied. The prey's body becomes an extension of the octopus's own sensory field. Each suction cup tastes, feels, and interprets. Resistance patterns are mapped like terrain. Within seconds, the beak engages. Venom enters the prey's bloodstream, interfering with sodium channels in nerve membranes, disrupting signal transmission. Paralysis follows not as brute shutdown, but as interference with the electrochemical language of muscle. Control shifts from physical restraint to biochemical domination. The prey's movements weaken, then cease. And yet, in some contexts, octopuses themselves become targets while engaged in such embraces. Sharks and larger fish may seize distracted individuals. The act of wrapping prey exposes the octopus to opportunistic predators. Camouflage is compromised during active feeding, and ink deployment while grappling is less effective. The hunter risks becoming hunted. This tension shapes behavior. Octopuses often drag captured prey back into dens before consuming them, minimizing exposure. These dens, littered with shells, reveal patterns of predation that influence benthic community structure. By targeting specific crab species, octopuses regulate population densities, altering grazing pressure on algae and shaping reef dynamics. The immobilization of one crab echoes outward into ecosystem balance. The fear associated with the octopus's grip stems from its comprehensiveness. Prey is not merely struck, it is enveloped in a multisensory net that anticipates resistance. The distributed intelligence of arms allows the octopus to solve mechanical puzzles in real time. A crab's claw lifted defensively is rotated gently until it cannot exert force. A fish's gill cover is pressed closed, reducing oxygen intake. Every movement is counted before it becomes effective. Softness, once perceived as vulnerability, reveals itself as strategic superiority. Without rigid bones, the octopus molds to the prey's shape, eliminating gaps that could serve as escape routes. The absence of skeleton allows infiltration into narrow crevices, extending control beyond visible boundaries. What seems fragile is in fact adaptive fluidity. In the quiet aftermath, the octopus resumes stillness. Arms retract, camouflage returns, and the predator dissolves back into rock. The violent seizure leaves no trace except discarded shells outside a den. The ecosystem resets, awaiting the next unsuspecting wanderer. Control in the ocean often belongs to those who dominate space rather than distance. The octopus does not chase relentlessly. It waits, then collapses possibility into inevitability. When its arms close, escape routes vanish not because they are blocked, but because they are absorbed into a living net of muscle and nerve. The prey's fear is the sudden realization that movement no longer answers to its own commands. In that instant, the ocean's fluid openness transforms into confinement. And within that confinement, the octopus reigns, not through brute strength alone, but through the intimate mastery of touch and pressure. The pull is sudden, sideways, and absolute. One moment a reef fish hovers inches above coral, fins flickering in effortless suspension, and the next, the world narrows into a crack no wider than its own body. Jaws clamp down not to sever, but to anchor. The Moray eel does not chase into open water, does not spiral in pursuit like a barracuda or accelerate like a shark. It retreats. It pulls. And in that retreat lies the true violence. The prey is not simply bitten. It is taken somewhere the reef itself becomes a weapon. Moray eels are architects of confinement. Their elongated bodies are designed not for sprinting, but for infiltration, slipping between coral branches and into limestone cavities where daylight dissolves into shadow. The skull is narrow, yet reinforced, capable of withstanding lateral torsion as the eel twists within tight corridors. Rows of backward curving teeth line the jaws, preventing prey from sliding free once seized. But the most remarkable feature hides deeper inside the throat. A second set of jaws, pharyngeal, capable of lunging forward to grip prey and drag it inward. This mechanism ensures that escape, even after initial capture, becomes mechanically improbable. The reef is not merely backdrop. It is infrastructure. Coral formations create labyrinths of channels and overhangs, spaces too confined for most fish to maneuver once momentum is disrupted. A fish adapted for open water evasion relies on lateral bursts, tail beats that generate rapid acceleration across distance. Inside a crevice, distance vanishes. The body collides with stone. Fins scrape against rock. Turning radius collapses. The environment itself absorbs movement. Moray eels exploit this geometry with precision. They wait with only a head protruding from a hole, body coiled within the cavity, sensory pores along their snout sampling chemical traces in the water. Vision plays a lesser role here. Olfaction dominates. The eel detects amino acids dissolved in current, reading prey presence through scent gradients invisible to sighted animals. When a fish ventures too close, the strike is short and explosive. jaws snapping with sudden force. But instead of thrashing in open reef, the eel reverses, pulling backward into darkness. The fear is not the initial pain. It is the spatial collapse. Light fades as the fish is dragged deeper into a tunnel it cannot see. The reef walls press inward, removing lateral escape paths. Water flow becomes restricted, reducing the prey's ability to orient through current cues. The eel's body, anchored within its chosen cavity, uses leverage from rock surfaces to generate pulling force far beyond what it could produce in open water. Each backward undulation wedges it more securely into the crevice, converting its surroundings into a fulcrum. Inside that darkness, the pharyngeal jaws advance. Unlike most fish, whose secondary jaws merely assist in swallowing, morays project theirs forward in a rapid extension that clamps onto prey and retracts, ratcheting the fish deeper into the throat. This adaptation compensates for the eel's narrow head and limited suction-feeding capability. Instead of engulfing prey through water displacement, it grips and pulls in stages. Escape becomes a mechanical impossibility once the inner jaws engage. The reef's microenvironment compounds the crisis. Tight spaces reduce oxygen circulation, increasing physiological stress on prey already struggling against restraint. Elevated carbon dioxide levels in confined water can disrupt acid-base balance in fish blood, impairing muscle function. As panic accelerates respiration, oxygen depletion hastens fatigue. The prey's own metabolic surge works against it. And yet this strategy carries its own vulnerabilities. Moray eels, for all their fearsome reputation, are not dominant in open water. Their elongated bodies lack the hydrodynamic efficiency of pelagic predators. They cannot pursue fleeing prey across distance with sustained speed. Their reliance on crevices reflects an evolutionary trade-off: power within confinement at the expense of open-field agility. In the bright, exposed reef crest, morays are cautious, often retreating from larger predators such as groupers or sharks. This is the narrative reversal. The darkness that spells doom for prey is also the moray's dependency. Remove the labyrinth of coral, and the eel's advantage diminishes sharply. In degraded reefs where coral cover declines due to bleaching or storm damage, hiding spaces shrink. Morays become more exposed, their ambush sites reduced. Their hunting success declines as structural complexity erodes. Within intact reefs, however, the eel's partnership with the environment extends beyond passive shelter. Some species engage in cooperative hunting with groupers, a phenomenon that blurs traditional predator hierarchies. The grouper, powerful in open water, signals to a moray with headshakes and body language, recruiting it to flush prey from crevices. The moray penetrates tight spaces inaccessible to the grouper, driving hidden fish into open water where the larger predator can strike. Here, darkness and light function as alternating traps, prey shuttled between realms of disadvantage. The eel, once perceived as solitary and confined, becomes part of a dynamic hunting network. Yet even in solitary hunts, the eel's strategy depends on environmental architecture. Coral reefs are three-dimensional mosaics shaped by centuries of calcification and erosion. Each cavity offers microhabitats that concentrate prey species seeking shelter from their own predators. By positioning itself within these intersections of traffic, the moray leverages ecological patterns to its advantage. It does not need to roam. It occupies a node in a network of movement. The prey's perspective is shaped by that same architecture. Reef fish rely on familiarity with terrain to evade predators, darting into holes they have memorized. But familiarity can betray. The very crevice that once offered safety may house a waiting eel. Behavioral ecology teaches that shelter selection involves constant risk assessment. Fish must balance protection from open water hunters against exposure to ambush predators within refugees. The reef offers safety, but not universally. As the eel tightens its hold inside the crevice, the mechanical act of consumption unfolds with clinical efficiency. Teeth prevent backward motion. Inner jaws advance and retract rhythmically. The eel's body undulates against rock, using friction to anchor itself while generating pulling force. The prey's struggles weaken as oxygen debt accumulates and muscular exhaustion sets in. Darkness becomes complete. Yet the story does not end with inevitability. Certain prey species have evolved strategies to counter crevice predation. Cleaner fish, for example, often operate in mutualistic relationships with larger predators, reducing attack likelihood through established behavioral contracts. Some reef fish secrete mucus layers that reduce grip efficiency. Others adopt body shapes too broad for narrow cavities, limiting their vulnerability to being dragged inward. Even the timing of foraging, remaining in open water during peak Moray activity, reflects adaptive responses to this specialized predator. Morays themselves must navigate the constraints of their chosen environment. Inside tight crevices, mobility is restricted. If a larger predator attempts to extract them, retreat options are limited. Their reliance on darkness is double-edged. The same tunnels that amplify their power can become traps if the reef structure shifts or collapses. The reef remains the silent protagonist in this encounter. Its branching corals, overhangs, and rubble fields dictate who controls movement and visibility. In open sand flats adjacent to reefs, morays are rarely encountered hunting. They return to the labyrinth, to the architecture that transforms them from elongated fish into masters of confinement. For the prey, the terror lies not in the sharpness of teeth, but in the sensation of being relocated beyond light and leverage. Movement ceases to function as escape. Visibility narrows to nothing. The reef that once promised protection becomes a corridor leading inward, deeper, darker. And yet, across the reefscape, balance persists. Morays regulate populations of smaller fish, preventing overgrazing of coral polyps and maintaining ecosystem stability. Their predation contributes to trophic equilibrium, shaping species composition over time. The act of dragging prey into darkness reverberates outward into reef health and biodiversity. As currents shift and light angles change with the sinking sun, the Moray's head once again protrudes from its chosen cavity, jaws opening and closing rhythmically to ventilate gills. It appears almost passive, an unmoving presence within rock. But beneath that stillness lies a strategy refined by evolution. Do not chase the world. Let the world come close, then remove it from sight. The reef returns to its quiet choreography of grazing and gliding. Fish weave through coral branches, confident in familiar terrain. Yet somewhere within that maze, darkness waits not as absence of light, but as controlled space. And in that space, the Moray reigns, not by dominating open water, but by mastering the places where escape becomes impossible. The water is perfectly still when it happens. A shoal of sardines drifts in tight formation, bodies aligned in subtle synchrony, each fish adjusting position by fractions of a fin stroke in response to neighbors. Sunlight filters through the surface in shifting columns, and suspended plankton flickers like dust in a cathedral of blue. There is no tremor, no ripple of warning. Then the stillness ruptures. A silver lance tears through the shoal with such speed that motion registers only as absence. One sardine is gone before the school can contract. The Barracuda has already passed. Barracuda do not advertise intent. Their bodies are built like projectiles, elongated, rigid, streamlined to reduce drag in the densest medium short of rock. Large jaws extend forward, armed with interlocking dagger-like teeth designed not for grinding, but for slicing. The musculature along the flanks is dense with fast twitch fibers, capable of explosive contraction, but unsustainable for prolonged effort. They are sprinters of the pelagic corridor, organisms optimized for the fraction of a second when acceleration eclipses perception. The strike begins long before it is visible. Barracuda hover in apparent inertia, maintaining position with minimal fin movement, reducing hydrodynamic noise. Their eyes are forward-facing and disproportionately large relative to body size, maximizing binocular overlap and depth perception. In clear tropical waters where they often patrol, visibility can extend dozens of meters, and contrast becomes the primary cue. A flicker within a shoal, an individual slightly out of alignment, becomes a target. The Barracuda's brain does not deliberate in the human sense. It calculates trajectory based on vector and velocity, solving interception geometry through neural circuits honed by repetition. When propulsion engages, the caudal fin snaps in rapid oscillation, and the body stiffens into a living spear. Water shears along the flanks as the fish accelerates, exploiting the inertial advantage of mass and momentum. The prey does not experience gradual escalation. There is no drawn-out chase to interpret. The first sensory cue is often pressure displacement, too late to matter. By the time lateral line receptors detect the approaching wave, the predator's jaws are already closing. Reaction time in small fish is limited by neural conduction speed and synaptic processing. Even the most vigilant sardine requires milliseconds to translate sensory input into muscular response. Barracuda strikes compress that window to near zero. The predator's velocity outpaces the prey's neurological threshold. The impact is instantaneous. The fear, in biological terms, is the impossibility of preemptive avoidance. Yet the ecosystem surrounding this interaction complicates the narrative. Sardines and other schooling fish are not naive victims drifting in ignorance. Schooling itself is an evolved response to predation pressure. By aligning bodies and maintaining tight spacing, individuals reduce per capita risk through the confusion effect. Predators targeting a mass of similar shapes struggle to isolate a single trajectory. In theory, the school functions as a living shield. Barracuda, however, exploit edges. They do not plunge blindly into the densest core. They target the periphery, where alignment falters. The fish on the margin carries disproportionate risk, a fact that drives constant micro-adjustments within the shoal. Each sardine attempts to remain centrally positioned, producing a dynamic flux of bodies that appears smooth from afar, but is internally competitive. The predator leverages that competition. Hydrodynamics plays a role as well. When a barracuda accelerates, it generates a bow wave that can disrupt the cohesion of the shoal. Fish nearest the impact zone scatter reflexively, creating momentary gaps. Those gaps amplify vulnerability, and in the chaos of dispersal, a second strike may follow. Barracuda do not rely solely on surprise, they capitalize on fragmentation. Stillness, then, is not passivity, it is strategy. By minimizing motion before attack, the barracuda reduces detection probability. Many prey species rely on relative motion against background to identify threats. A stationary predator blends into the visual field, especially when countershaded, dark above, pale below, to match light gradients. The ocean's brightness compresses color into silvers and blues, making a hovering barracuda nearly invisible until it moves. And yet, here lies the reversal. The barracuda's reliance on speed imposes metabolic costs. Fast twitch muscle fibers generate rapid bursts of power, but accumulate lactate quickly, limiting endurance. A failed strike demands recovery time. Repeated misses can deplete energy reserves critical for survival in nutrient-variable waters. Unlike tuna, whose red muscle supports sustained cruising, barracuda depend on ambush efficiency. Precision is mandatory. Prey exploit this limitation. Some species adopt erratic swimming patterns rather than uniform alignment, reducing predictability of trajectory. Others seek refuge in structurally complex habitats, coral heads, mangrove roots, where a high-speed predator cannot maneuver without risk of collision. In such environments, the barracuda's greatest asset becomes liability. Rigid bodies, optimized for straight-line acceleration, struggle in tight spaces. Moreover, larger predators lurk beyond this exchange. Sharks and groupers may view barracuda themselves as prey or competitors. In open water, the barracuda's silver flash during a strike can attract attention. A predator fixated on smaller fish may suddenly find itself pursued. The hierarchy is fluid. The speed that terrifies sardines is not universally dominant. Still, in the open blue where structure fades and schools shimmer like liquid metal, the barracuda's method reigns. The moment before reaction defines the encounter. Prey drift within an illusion of safety, sustained by collective vigilance. The predator waits, muscles coiled beneath skin that reflects ambient light. Then physics intervenes. Acceleration in water requires overcoming drag proportional to velocity squared. Barracuda achieve this through powerful caudal peduncles and streamlined profiles that minimize turbulence. Their scales lie flat, reducing boundary layer disruption. The first few tail beats are decisive, generating the thrust necessary to close distance before prey can scatter fully. Jaws open at precisely timed intervals to maximize gape upon contact. Impact is not always lethal on first contact. The serrated teeth are designed to slash, often severing prey into manageable sections. The barracuda may strike through a shoal, then wheel sharply to consume injured fish trailing behind. The violence appears chaotic but follows predictable patterns of biomechanics and opportunity. In the aftermath, the water regains stillness. The shoal reforms, closing ranks as if nothing occurred. Evolution demands resilience. Constant panic would exhaust energy reserves. Instead, fish recalibrate spacing and resume feeding. The barracuda, having expended its burst, returns to hovering vigilance, muscles relaxing, respiration steadying as oxygen debt resolves. This cycle repeats countless times across coral reefs and coastal shelves. Barracuda regulate mid-level fish populations, influencing grazing pressure on plankton and algae. Their presence shapes shoaling behavior, which in turn affects nutrient distribution and predator-prey dynamics at multiple levels. The single strike ripples outward through ecological networks. What distinguishes the barracuda is not brutality, but temporal compression. It condenses predation into an instant so brief that cognition lags behind consequence. Prey live in a perpetual edge of potential impact. Their neural circuits tuned for detection, yet perpetually racing against a predator optimized to outrun thought itself. The ocean's calm facade masks these fractions of violence. Sunlight dances, currents drift, schools glide in hypnotic unison. Somewhere within that serenity, a predator holds position, perfectly aligned with the physics of speed. There will be no warning call, no ripple to interpret in time. Only the sudden rupture of water and the vanishing of one silver body. And then, once more, stillness. The circle closes so gently that nothing feels wrong at first. A juvenile damselfish hovers above coral rubble, inspecting a patch of algae, aware of currents and neighbors, but sensing no immediate alarm. There is no explosive surge, no sudden shadow slicing through the water column. Instead, elongated fins begin to unfurl nearby, thin rays spreading like the delicate ribs of a fan. The lionfish does not charge. It expands. Lionfish hunt with architecture rather than speed. Their bodies are draped in venomous spines and trailing fin membranes that extend outward in wide arcs, transforming a relatively compact predator into a moving wall of striped geometry. These fins are not mere decoration. They are behavioral tools. By slowly spreading them, the lionfish creates a visual barrier that narrows the prey's perceived escape corridor. The damselfish continues to hover, reacting to subtle shifts in light and current. But the open water around it has already begun to shrink. Unlike ambush predators that rely on sudden acceleration, lionfish exploit cognitive blind spots in prey species. Reef fish are attuned to high-velocity threats. Their lateral line systems detect rapid pressure changes, and their eyes prioritize movement against background patterns. Lionfish approach at a deliberate pace, minimizing turbulence and avoiding abrupt displacement. To the prey's sensory apparatus, nothing urgent registers. The predator is simply part of the reefscape, its striped pattern blending with coral shadows and sea fans. As the lionfish advances, it positions itself with careful orientation, angling its body to corral the prey against a structural boundary, such as a coral head or rock face. Each incremental movement reduces available space. The damselfish senses confinement only gradually. It shifts left, then right, but the predator's fins adjust correspondingly, maintaining a soft but persistent pressure. Escape routes diminish not through violence, but through geometry. The venomous spines lining the lionfish's dorsal and pectoral fins add psychological deterrence to physical encroachment. While the venom is defensive rather than offensive, its presence discourages counterattacks from larger fish. Predators that might otherwise disrupt the hunt hesitate, wary of painful envenomation delivered through contact. The lionfish moves within a protective halo of toxicity, allowing it to focus entirely on constricting prey space. Inside this tightening perimeter, the prey's stress hormones rise. Cortisol levels increase in response to prolonged threat perception, altering metabolic priorities. Muscles prepare for flight, but flight requires direction. With each subtle adjustment of the lionfish's fins, directional clarity erodes. The damselfish's nervous system struggles to identify a viable vector. The predator has not struck. It has shaped the battlefield. Lionfish employ a secondary tactic that further destabilizes prey cognition. They may blow gentle jets of water toward the target, disturbing balance and forcing repositioning. This behavior is not random. It flushes the prey into positions more advantageous for final capture. The damselfish, correcting for unexpected currents, expends energy while inadvertently moving closer to the predator's mouth. The final phase unfolds with deceptive swiftness. Once the prey is confined within a narrow cone of space, the lionfish executes a short, rapid lunge, jaws opening to engulf the fish in a single suction-driven motion. The strike is brief, but it succeeds because the prey's escape options were dismantled long before the jaws moved. The fear here is cumulative. It is not the shock of impact, but the dawning realization that freedom of movement has been quietly erased. Ecologically, this hunting strategy reflects adaptation to complex reef environments where structural density limits long chases. Speed risks collision with coral and wastes energy in tight quarters. By reducing prey mobility gradually, lionfish conserve metabolic reserves while maximizing capture efficiency. Their hunting style is energetically economical, relying on precision rather than pursuit. Yet the story deepens when viewed through the lens of ecological imbalance. In native Indo-Pacific reefs, lionfish coexist with predators and competitors that modulate their population density. Groupers and sharks occasionally prey upon juvenile lionfish, and established reef fish recognize their presence as threat. The spatial trapping technique functions within a balanced web of checks and pressures. In invaded ecosystems such as the Western Atlantic, however, the absence of natural predators amplifies the lionfish's effectiveness. Native prey species lack evolutionary familiarity with its slow encroachment strategy. They fail to recognize the gradual confinement as imminent danger. This mismatch between predator behavior and prey perception leads to disproportionate predation rates, reducing populations of herbivorous fish that regulate algal growth. As algae proliferate, coral recruitment declines, and reef structure shifts over time. The lionfish's slow trap extends beyond individual prey to reshape entire communities. And yet the predator's dominance is not absolute. Certain prey species have begun exhibiting adaptive responses, altering habitat use and schooling behavior to mitigate lionfish encroachment. Increased vigilance and preference for open sand patches reduce the effectiveness of fin-based corralling. In some regions, human-led culling efforts introduce new selective pressures, reducing lionfish density and allowing reef systems to partially recover. There is also a physiological constraint embedded in the lionfish's method. Extended fin display increases drag, making the fish more conspicuous to larger predators and potentially limiting rapid retreat. While venomous spines deter many threats, they do not render the lionfish invulnerable. Large groupers have been observed consuming lionfish, circumventing spines through strategic positioning and powerful jaws. The narrative reversal emerges here. The same fins that create a cage for prey expose the lionfish to detection in open water. Its ornate silhouette, so effective in confinement, becomes a liability in exposed environments. Without reef structure to amplify its strategy, the lionfish's slow advance loses potency. Still, within coral labyrinths and rubble fields, the technique remains formidable. The damselfish's world narrows until options dissolve. Movement becomes futile, not because of speed, but because of space. The predator has transformed environment into instrument. Light filters across striped fins, casting shifting shadows that further confuse prey perception. The reef hums with subtle currents, unaware of the silent siege unfolding within its crevices. To an observer at distance, nothing dramatic occurs. Only a fish hovering near another fish. Yet within that calm facade, geometry is tightening. When the strike finally arrives, it feels abrupt, but it is merely the culmination of a process already completed. The lionfish resumes its slow patrol, fins folding partially, venomous spines still raised in quiet warning. Another small fish drifts among coral branches, unaware that the boundaries of its freedom can be erased without a chase, without a ripple, without a single explosive motion. In this reef theater, terror is patient. It does not announce itself with speed. It arrives through incremental narrowing, through soft barriers that feel like coincidence until they become confinement. And by the time realization dawns, the circle has already closed. The first contact does not look like violence. A juvenile fish darts through sunlit shallows, weaving between shafts of light and suspended particles, its lateral line reading faint pressure shifts, its eyes tuned to flickers of motion. There is no silhouette, no predator advancing with measurable speed. The water appears empty. Then something touches its flank, soft as drifting thread. In less than the span of a heartbeat, thousands of microscopic harpoons fire. The box jellyfish does not pursue. It does not close distance with muscle and bone. It waits in near transparency, a gelatinous cube suspended beneath the surface, tentacles trailing like forgotten filaments in the current. Its body refracts light rather than reflecting it, rendering edges indistinct. The bell pulses gently, not in pursuit but in repositioning, maintaining vertical orientation in shallow coastal waters where currents carry both plankton and unwitting prey. The terror lies in the absence of warning. The prey swims forward into an architecture it cannot perceive. Each tentacle is lined with millions of nematocysts, specialized cells containing coiled, venom-loaded tubules under extreme internal pressure. Mechanical and chemical triggers activate them. When a fish's skin brushes a tentacle, microscopic hairs detect contact and discharge is instantaneous. The tubule everts explosively, penetrating tissue and injecting venom within microseconds. There is no time for avoidance. The stimulus and consequence are fused. Venom from certain species of box jellyfish is among the most potent in marine ecosystems. It contains a complex mixture of toxins that disrupt ion channels in nerve and muscle cells, causing rapid depolarization and cellular damage. In small fish, this can induce paralysis almost immediately, interfering with gill movement and cardiac rhythm. The prey does not register a predator closing in. It experiences sudden systemic failure. Muscles that propelled it through water lose coordination. Fins falter. What makes this encounter uniquely terrifying is invisibility. Unlike predatory fish that generate pressure waves detectable through lateral line systems, the tentacles drift passively. Hydrodynamic disturbance is minimal. The box jellyfish's bell pulses slowly, often matching ambient current speed, reducing relative motion between predator and prey. To the sensory apparatus of a small fish, the environment remains unremarkable until contact triggers catastrophe. The box jellyfish's body plan reflects evolutionary minimalism combined with lethal efficiency. Its cube-shaped bell houses complex eyes, more advanced than many assume. Clusters of image-forming eyes allow it to detect light gradients and obstacles, guiding movement toward favorable habitats such as mangrove lagoons where prey density is high. It does not chase individual fish, but it positions itself strategically, using environmental cues to maximize encounter probability. In this sense, the predator relies on spatial intelligence rather than pursuit. Prey, for their part, are adapted to detect motion and contrast. Transparent or near-transparent organisms challenge these detection systems. The box jellyfish's tissues contain little pigment, minimizing visual footprint. Its tentacles, thin and almost invisible, blend seamlessly with shafts of light. Fish may interpret them as debris or filamentous algae, stimuli too common to trigger alarm. The ecological implications extend beyond individual encounters. Box jellyfish often occupy nursery habitats where juvenile fish congregate for shelter and feeding. Their presence can shape survival rates of early life stages, influencing recruitment dynamics in coastal ecosystems. A season with elevated jellyfish abundance can reduce fish populations that would otherwise grow to regulate invertebrate communities. Invisible contact cascades outward into visible ecological shifts. Yet within this apparent dominance lies vulnerability. Box jellyfish are fragile organisms, their gelatinous bodies susceptible to damage from strong turbulence or predation by certain species, such as sea turtles, which possess mucus-lined throats and specialized adaptations to tolerate nematocyst discharge. turtles consume jellyfish without succumbing to venom, reducing jellyfish density in some habitats. The same tentacles that immobilize fish prove ineffective against predators equipped with physiological resistance. Moreover, environmental conditions influence venom potency and hunting success. Changes in salinity, temperature, and nutrient availability affect jellyfish distribution and reproduction. In some regions, nutrient enrichment from human activity can lead to jellyfish blooms, amplifying their ecological impact. In others, habitat degradation may reduce their numbers. The invisible predator is intertwined with larger environmental dynamics. For prey species, adaptation emerges gradually. Some fish develop thicker mucus layers that may reduce nematocyst penetration. Others alter swimming depth or habitat preference during peak jellyfish seasons. Behavioral plasticity becomes a form of defense against unseen threat. Yet no adaptation fully eliminates risk. Contact remains a lottery with devastating odds. The box jellyfish's hunting method challenges common perceptions of predation. There is no dramatic chase, no display of speed or strength. Instead, it represents passive lethality, venom delivered through accidental encounter. Energy expenditure is minimal compared to active predators. The bell pulses maintain position and modest directional movement, but most of the work is done by current and chance. Evolution has shaped a system where the environment transports prey into the predator's reach. This strategy aligns with metabolic efficiency. Jellyfish lack complex musculature and do not invest heavily in high-energy pursuits. Their simple nerve nets coordinate basic movement patterns without centralized brains. They thrive in conditions where food encounters are frequent enough to sustain them without pursuit. In nutrient-rich shallows, this strategy proves highly effective. The narrative reversal emerges when considering that invisibility, the core of their advantage, also constrains them. Box jellyfish depend on water clarity and calm conditions to maintain effective tentacle deployment. In turbid or highly turbulent waters, tentacles may tangle or be damaged, reducing hunting efficiency. The same transparency that conceals them renders them delicate. They cannot withstand violent storms or abrasive contact with reef structures. Additionally, their venom, potent though it is optimized for small prey. Larger animals may experience pain and tissue damage, but are less likely to be immobilized. Humans, entering jellyfish habitats unaware, encounter the same invisible threat, illustrating how evolutionary defenses designed for fish can inadvertently impact other species. The box jellyfish does not distinguish. Contact triggers discharge regardless of target. Still, within the shallow lagoon where light dances across sand and mangrove roots cast shifting shadows, the predator remains nearly undetectable. Fish dart through the water column, feeding on plankton, unaware that transparent filaments hang like suspended lightning. The absence of chase lulls vigilance. The ocean feels open, navigable. Then a fin brushes a strand. The reaction is chemical and immediate. Paralysis ripples through muscle fibers as sodium channels lock open, disrupting electrical gradients essential for nerve signaling. The fish's world collapses not through visible assault, but through biochemical intrusion. The box jellyfish reels in its tentacles, drawing immobilized prey toward its central mouth, digestion beginning externally as enzymes break down tissue. The lagoon returns to quiet suspension. Nothing dramatic marks the encounter. No thrashing predator tears through water. Only a drifting cube, tentacles extended once more, awaiting the next accidental brush. Invisible danger defines this realm. It is not speed that terrifies, but absence of warning. In these waters, safety cannot be inferred from calm. Transparency conceals architecture of harm. And as fish continue to swim through shafts of light, the box jellyfish remains a silent presence, its lethal threads woven seamlessly into the fabric of the sea. The water explodes into motion before the prey understands why it is running. A school of sardines fractures mid-column, silver bodies flashing in tight synchronization, their muscles firing in rapid oscillation as they surge away from a shadow that does not slow. Behind them, a bluefin tuna drives forward with relentless propulsion, its crescent tail scything through the water in a rhythm engineered for endurance rather than spectacle. There is no sudden ambush, no single decisive strike. The pursuit has already begun, and it will not end quickly. Tuna are not hunters of surprise. They are hunters of inevitability. Their bodies are built for sustained speed across vast distances, with a fusiform shape that minimizes drag and a powerful caudal peduncle anchoring one of the most efficient propulsion systems in the marine world. Unlike many fish that rely on short bursts fueled by anaerobic metabolism, tuna maintain high cruising speeds through a remarkable adaptation known as regional endothermy. Specialized heat exchangers called retia mirabilia conserve metabolic heat generated by red muscle tissue, elevating body temperature above surrounding water. Warmer muscles contract more efficiently, allowing tuna to sustain velocity while competitors fatigue. The sardines do what evolution has taught them. They cluster into a bait ball, compressing into a rotating sphere that confuses predators by presenting a wall of synchronized movement. This collective defense exploits the predator's targeting systems, making it difficult to isolate an individual. But tuna do not depend on isolating prey in the first moments. They slice through the periphery, forcing the school to shift, to compress, to expend energy. Each evasive maneuver costs glycogen reserves. Each acceleration erodes endurance. The chase is not chaotic, it is strategic pressure applied over time. Tuna often hunt cooperatively, corralling schools toward the surface or into confined spaces where escape vectors narrow. By alternating bursts of acceleration with sustained cruising, they maintain proximity without exhausting themselves. Their cardiovascular system, supported by a large heart and dense capillary networks in red muscle, delivers oxygen efficiently, delaying fatigue. The sardines, lacking such thermal and metabolic advantages, begin to falter. Fear in this scenario is not the shock of sudden capture, but the creeping realization that distance does not equal safety. A sardine that slips free of the main cluster finds open water, only to detect pressure waves behind it once more. The predator has not disengaged. Tuna possess acute vision adapted for both brightness and depth, enabling them to track individual fish even as light conditions shift. They recalibrate trajectory with precision, adjusting tail beats to maintain optimal thrust-to-drag ratios. The hydrodynamics of pursuit matter profoundly. Tuna reduce drag through retractable fins that fold into grooves along their bodies, streamlining their profile during high-speed chases. Their skin, coated in mucus, further decreases friction. These adaptations transform sustained pursuit into an energetically viable strategy. The predator does not gamble on a single explosive lunge. It invests in duration. As minutes stretch, the sardine's anaerobic capacity reaches its limits. Lactic acid accumulates in muscle tissue, impairing contraction efficiency. Respiratory rates spike as gill ventilation struggles to meet oxygen demand. The school's cohesion begins to fragment under metabolic strain. Tuna sense this weakening through subtle changes in schooling dynamics, honing in on individuals whose swimming patterns become erratic. Then comes the shift in tempo. A tuna accelerates, not from rest but from sustained velocity, amplifying its already formidable speed. The prey, already depleted, cannot match the renewed surge. Capture occurs not because the predator was faster in a single instant, but because it outlasted its target. The final bite is swift, but it is the culmination of sustained attrition. Ecologically, this hunting style exerts pressure on prey populations in ways that shape schooling behavior and migration patterns. Sardines and other small pelagic fish must balance feeding opportunities with predator avoidance, often traveling in dense aggregations that reduce individual risk but increase collective visibility. Tuna, in turn, track these aggregations across vast oceanic expanses, migrating seasonally in pursuit of shifting prey distributions. Their endurance allows them to traverse entire basins, linking ecosystems separated by thousands of miles. The narrative reversal emerges when considering that this relentless hunter is itself bound by endurance constraints at a planetary scale. Tuna require high oxygen concentrations to sustain their elevated metabolic rates. Ocean warming reduces dissolved oxygen levels in some regions, compressing suitable habitat vertically and geographically. The very physiology that grants tuna dominance also ties them to narrow environmental parameters. In waters depleted of oxygen, their endurance advantage diminishes. Moreover, tuna are among the most heavily targeted fish by industrial fisheries. Longlines and purse seines intercept migratory routes, applying a different kind of sustained pressure. The hunter becomes the hunted, pursued across open oceans by vessels equipped with sonar and satellite tracking. Their speed, once a shield against natural predators, offers limited defense against technological pursuit. Yet within the chase itself, the tuna's adaptations remain extraordinary. Their red muscle fibers, rich in myoglobin, store oxygen efficiently, supporting prolonged aerobic activity. Their large gill surface area facilitates rapid gas exchange, and their streamlined morphology reduces energy expenditure per unit distance traveled. Every anatomical detail converges toward a singular strategy: never stop. For the sardine, the terror is cumulative. It is not a shadow that vanishes after a missed strike. It is a presence that persists, adjusting pace, recalibrating distance, waiting for fatigue to tip the balance. Escape becomes a temporary reprieve rather than a solution. The predator's patience transforms time into a weapon. Even in the vast openness of the pelagic zone, where there are no coral heads or mangrove roots to constrain movement, confinement emerges through exhaustion. The ocean offers space, but space does not equal sanctuary when the pursuer matches every turn. The tuna's body, shimmering blue and silver, cuts through the water with mechanical consistency, its muscles warm and primed. As the sardine's energy reserves collapse, its swimming pattern stutters. The school no longer moves as a single organism, but as scattered fragments. The tuna senses vulnerability and commits to the final acceleration. Jaws open, engulfing prey in a decisive snap that ends a pursuit measured not in seconds, but in sustained pressure. The sea calms. The predator resumes its steady cruise, scanning for the next aggregation. There is no frenzy, no display of dominance, only the quiet confidence of a creature built to endure. In this realm, fear is not the instant of impact, but the knowledge that the chase will not cease. The predator will not tire first. The ocean is vast, but stamina reshapes its boundaries. And somewhere ahead, another school senses disturbance in the water, unaware that distance alone will never be enough. The reef corridor collapses into a maze of stone and shadow, and in the space between two coral buttresses, a slender head appears without warning. A parrotfish reverses too late. There is no distant silhouette, no gradual approach across open water. The predator is already inside the architecture, already within striking range. In tight reef spaces, distance is measured in body lengths, and survival is decided in fractions of a second. The sea snake does not need pursuit when the walls themselves compress the encounter. Sea snakes are built for confinement. Their bodies are laterally compressed like ribbons, allowing them to slip between branching corals and beneath overhangs where bulkier predators cannot follow. The paddle-shaped tail provides precise maneuverability rather than raw speed, enabling controlled turns in spaces where a single miscalculation would mean collision. Unlike pelagic hunters that rely on velocity across open water, sea snakes exploit geometry. The reef is not an obstacle. It is an amplifier. The parrotfish senses turbulence only after the snake's body has already curved around a coral spur. Vision in reef fish is tuned to detect movement against complex backgrounds, but in these tight corridors, movement and structure blend into a single field of shifting color. The snake's patterned scales mimic the broken light of reef surfaces, disrupting its outline. Camouflage here is not about invisibility across distance. It is about confusion at arm's length. Then the strike. It is not dramatic in amplitude, but devastating in proximity. Sea snakes possess fixed front fangs connected to venom glands that deliver potent neurotoxins. These toxins interfere with neuromuscular transmission, binding to receptors at the synapse and preventing muscle contraction. In open water, a fish might attempt to flee after envenomation. In a reef crevice, escape vectors are blocked by limestone walls and living coral. Paralysis in confined space is not merely weakness, it is entrapment. Limited space alters behavior for both predator and prey. Reef fish often rely on rapid bursts of acceleration to reach shelter. Their bodies are designed for explosive anaerobic output, allowing sudden darts into crevices. But when the predator originates from within those same crevices, the defensive reflex collapses. Shelter becomes threat. The reef's labyrinthine complexity, typically a refuge from larger hunters, turns into a trap when occupied by a slender, venomous specialist. Sea snakes have evolved lungs that extend nearly the length of their bodies, functioning not only for respiration, but also for buoyancy control. By modulating lung volume, they achieve fine-tuned positioning within the water column, hovering in place without constant tail movement. In narrow passages, this stability allows them to remain motionless, conserving energy while awaiting movement from unsuspecting prey. The predator does not advertise its presence through unnecessary motion. The tension in these encounters is spatial. In open ocean, prey may calculate distance and trajectory. In a reef corridor barely wider than the predator itself, options vanish instantly. A fish turning left meets stone. Turning right meets living coral branches. Reversing risks collision. The sea snake exploits this compression, striking when the prey's escape calculus fails. Yet within this apparent advantage lies a constraint. Sea snakes are air-breathing reptiles tethered to the surface by physiological necessity. Their dives are limited by oxygen stores, and in the most intricate reef interiors, reaching the surface quickly can be challenging. The same narrow spaces that favor ambush can complicate retreat. A snake that ventures too deeply into branching coral risks entanglement or delay during ascent. Moreover, their venom, optimized for small fish and eels, is metabolically costly to produce. A failed strike represents wasted biochemical investment. Unlike predators that can rely on brute force capture, sea snakes must balance precision with restraint. They cannot afford indiscriminate biting in confined quarters. The narrative reversal emerges when considering that many reef fish recognize sea snakes not solely as predators, but occasionally as inadvertent allies. As sea snakes probe crevices for prey, they flush out small crustaceans and fish that other predators capture. Groupers and jacks may trail sea snakes at a cautious distance, exploiting disturbance caused by the serpent's search. The solitary hunter becomes part of an opportunistic network, its presence triggering secondary predation events. In some ecosystems, cleaner fish approach sea snakes, removing parasites from their scales. The venomous hunter, capable of lethal strike, tolerates these small attendants. Close-range danger coexists with intimate symbiosis. The reef compresses interactions not only into conflict, but into cooperation. Still, for the parrotfish caught in the corridor, there is no alliance. The venom spreads rapidly, disrupting muscular control. Gill movements slow. The snake's jaws, though relatively small, secure the immobilized prey. Swallowing begins headfirst to streamline ingestion within tight space. The predator must consume quickly before oxygen depletion demands ascent. The reef returns to deceptive calm. Coral polyps extend tentacles into the current, filtering plankton. Small fish resume grazing along surfaces. Yet within this intricate architecture, tension persists. Every crevice may conceal a ribbon of muscle and toxin. Sea snakes represent a fusion of terrestrial ancestry and marine specialization. Their scales reduce friction against coral, and their salt glands excrete excess sodium, allowing prolonged residence in saline environments. They embody evolutionary compromise, carrying lungs in a realm dominated by gills. That compromise shapes their behavior. They hunt efficiently within constrained spaces, but must always account for the vertical axis leading to air. Predators of sea snakes exist as well. Large sharks and certain raptors target them, immune or resistant to their venom. In open water, the snake's slender form offers little defense beyond toxicity. Thus, the reef's complexity not only aids hunting, but provides protection from larger threats. Confinement is both weapon and shield. In the end, close-range danger defines the sea snake's domain. The reef is not a backdrop, but an instrument, narrowing movement until encounter becomes inevitable. Prey do not experience a prolonged chase or distant silhouette. They encounter a predator already within their chosen refuge. The fear is immediate, born of proximity rather than pursuit. And as light filters through coral branches, illuminating suspended particles, the reef appears tranquil once more. Yet, within its corridors, space itself conspires with venom, compressing possibility into a single irreversible moment.